sisters once again. Sì, prova. 1, 2, 3, 4. Come?
Buongiorno a tutti. Rappresento qui oggi sia l'Accademia Nazionale dei Licei che ci ospita, sia il Consiglio della Fondazione Balzan Premio che organizza questa annuale riunione. Now I speak English because usually I start always in Italian because I have in the back of this screen I have Galileo Galilei and Prince Cesi, who at that time spoke Latin, and in fact our fundamental law called Lynciographum is in Latin. I cannot speak Latin, maybe that someone of the prize committee speaks Latin, but I don't speak Latin now. Professor Antonelli, who should be here with us this morning, cannot be because he has got a flu and is at home. Sorry, I've got someone? No, sorry. So Professor Antonelli told me to present her congratulations for this meeting, which is really very important one. Yesterday, I talked for a while shortly. Sorry? I disturb you, someone? Okay. So, I talked shortly about the Interdisciplinary Forum. It was not my duty to talk about this forum because I am the chairman of the board and not the chairman of the committee, General Price Committee. But I have to stress that yesterday, outstanding personality who were here with us consider it extremely important, this kind of initiative of Balzan. And in a certain way, they confirmed that the Interdisciplinary Forum of Balzan Prize winners, as far as they know, is a kind of unique characteristic of such important prizes. So I'd like to tell you that this outstanding personality of the institutional representation of the different position in the state, Italian state. Yesterday we had the President of the Republic, of course, the Vice President of the Upper House, the Vice President of Constitutional Court, the Vice President of the Lower House, and finally a fellow who is a colleague of us, the Ministry of Education. And many of these persons, having heard about the Interdisciplinary Forum, said that it is a very, very interesting initiative. I have nothing more to add because it's not my role today to make some consideration about the forum. The chairman is Professor Maiani. But of course, I stress again the pleasure and the honor to having here at Lincei this meeting on Balzan Foundation. I think that in the past years, Balzan and Lincei have had very useful collaboration, and Balzan and the Swiss Academy of Science and Humanities had very, very good collaboration. I have to remember here when this kind of collaboration with the two academies, national academies, started, because at the origin of this, there have been a meeting in the Swiss-Italian Alps among me, Suzanne Verder, Professor Denlinker, and Dr. Zürcher. And just to tell you, which is a kind of memory of all people, we met in Pontresina, which is in Graubünden, to discuss the possible collaboration among these three institutions, Balzan, Swiss Academy, and Accademia dei Lincei. And as far as I can judge, this collaboration and the alternation, the change every year, one in Bern and one in Rome, has given remarkable results. So I stress again this important collaboration between the Association of Swiss Academies and the Italian National Academy, and I like to stress also that this collaboration started in Graubünden, which is a very important canton of Switzerland. I think very important as far as I know it, and I know very well. Having said that, the floor is to Professor Maiani, and good work.
Thank you very much, Alberto, Professor Quadrio Curzio. And now we can go to our work, and it's a pleasure to be here. Welcome to everybody. And I would like to introduce Sirk Klöting, member of the General Prize Committee, who's going to introduce the first prize winner of the day, Susan Trumbor. Please.
Thank you, Luciano. Good morning, ladies and gentlemen. It is a great pleasure to introduce to you Susan Trumbord, recipient of the Balzan Prize 2020 for Earth System Dynamics. Susan received this prize for her outstanding contributions to the study of the carbon cycle and its effect on climate, and for pioneering the use of radiocarbon measurements in Earth system research. Her early work on the input of carbon-14 bomb pulse as a transient tracer that is now present at different concentrations in different components of the global carbon system has been a true breakthrough. She not only provided many of the initial insights into the use of this tracer, but also developed the technology that allowed its measurement. She is the leading authority on applying radiocarbon dating to environmental science, including climate change research, a topic today more important than ever. Her research is highly interdisciplinary, so it's very appropriate to start this forum with her presentation. She is connecting in her research ecology, plant physiology, and soil science, and of course the research is very global in scope. The outcomes of her research are important to assess the potential to manage soils, to store more carbon, to mitigate atmospheric carbon dioxide rise. Again, a topic very important in today's agenda, also in relation to the energy transition. She is a member of several prestigious academies, including the US National Academy of Sciences, the German National Academy Leopoldina, and Academia Europaea. She presented a month ago a wonderful Balzan Prize lecture at the annual conference of Academia Europaea. She serves as a role model for the young scientists, and she is very engaged in coaching them, also in the less research-intensive countries. So we are all looking forward to a presentation today, which will be on dynamics of land carbon cycle. Susan, the floor is yours.
Thank you very much for the kind introduction, Sarah, and thank you again for having to the Foundation and Prize Committee for selecting me to speak today. And so I'm going to talk to you about the land carbon cycle, and in particular, I'm going to focus on tropical research. Okay. And just to give you a roadmap, I want to do three things, and I have my timer, so I don't take too long to do it. The first one is to give you an idea of the changing carbon cycle and pick the part that land plays in that. The second is to give you a flavor of how we use radiocarbon to help understand the land carbon cycle. It's our clock for understanding. And the third is to give you I just wanted to take some time to introduce the Balzan Prize project that we've already begun, because the award was a year ago. So I want to give you a flavor, what our goals are and what our accomplishments are. So yesterday, as I said, in my lifetime, the rise in carbon dioxide, which is the red line there, in the last 60 years, has risen 100 parts per million. And if we compare that to the record from ice core bubbles, the carbon dioxide concentration has bounced up and down 100 parts per million between glacial cold periods and interglacial periods. So it's clear carbon dioxide and climate are interlinked, and we should expect warming. And also, temperatures have risen in our lifetimes by about 1 degree Celsius, and we're arguing between another ½ degree, which is pretty much baked into the system right now, and 2 degrees, but if we continue as we are, it could be as high as 4 degrees. So the point is that we as people, but also the plants and organisms living on the planet, we're all living outside the conditions that we've evolved with over the last millions of years. And we don't actually totally understand what the consequences of that will be. The rates of change are much faster than they were from the transition from glacial to interglacial. So they're, short of asteroid impacts, they're kind of unprecedented in geologic history. So the carbon cycle defines the natural exchanges of carbon dioxide between land, atmosphere, and ocean, and also the chemical transformations that a carbon atom will be in a CO2 molecule in the atmosphere. It gets fixed by a plant, and then it becomes a myriad of organic molecules that we find in all the plants and animals around us. This is since I was a graduate student, we've been trying to account for where the carbon dioxide that we burn and put into the atmosphere that sort of imprints on top of those natural cycles, where does it go? And so right now, this is the latest, there's a carbon cycle group that puts these budgets together every year now. You can find them online. Now we emit about 11 billion metric tons of carbon dioxide to the atmosphere per year. 85% of that is burning of fossil fuels, which we know because of economics. 15% is estimated to be from deforestation, and those are highly uncertain fluxes. Where does it go? Well, luckily the atmosphere has to mass balance. The carbon we put in has to go somewhere. So we can measure the increase of carbon dioxide in the atmosphere very accurately, so we know this, but it's only about half of what we're putting in. So where does the rest go? Well, carbon dioxide reacts with seawater and dissolves in seawater, and so that's a physical, chemical process. So we have observations of the chemistry change, the pH of the oceans is decreasing, and we also have models that can move that carbon around and lock it away from the atmosphere. So we're pretty confident that about a quarter is going into the ocean. So that leaves the rest. So it has to mass balance, so the rest must be going on land, and that's how we know the terrestrial carbon sink. It's higher than the estimates of deforestation, but it's uncertain, as are the estimates of deforestation. And we can have a network of global observation stations that look at small changes in CO2 from one place to the other. And that tells us that the tropics, especially tropical forest regions, are one of the places for sinks. Also, you can see the sinks in the eastern North America and Europe. Those are largely due to this next process. So they're, what is causing land to net remove carbon from the atmosphere? One is the regrowth of forests that were previously deforested. So I picked the map of Italy here from 1900 with estimates of forest cover. And you can see it's greener in 2010 than it was in 1900. And if you look at paintings of central Germany during the time of Goethe, as I do now, living in Jena, and you look at the place now, there's a lot of forest regrowth. And so some of this land sink, probably at least half of it, is regrowth of forest it's taking back carbon that was put in the atmosphere many years ago. The second major uptake is thought to be due to the fact that if we have a plant and we grow it in a different CO2 atmosphere, the more CO2 we have, the greater the rate of photosynthesis. And so this is a picture of an experiment. There's just been an experiment to do this in Brazil, which is the biggest uncertainty of whether CO2 fertilizes plants. And the question is really, how big is this and how important is it? The second major feedback between climate and the land carbon cycle is that warming will increase rates of decomposition, and so return of carbon to the atmosphere. So you just have to take something out of your refrigerator and put it on the counter to know that decomposition is faster when it's warmer. And the real question, especially now, is what happens at high latitudes where you take it out of the freezer. and put it on the counter so that we're melting permafrost at rates, again, that are probably much faster than they would have happened naturally. So if we put all this understanding together, our best understanding is what we make our models out of for the global level. And this is the prediction. It's old now, but the latest predictions are the same. They're the intercomparison of the carbon climate models that are used to predict the carbon dioxide levels in the future. So the biggest uncertainty is what people will put in the atmosphere. But this is telling us what the land carbon uptake will be going forward in time. So it goes from 1860 to 2100, but the predictions, you can see starting around now, the predictions go all over the place. These models have these two major feedbacks, the CO2 fertilization, which leads to the very large carbon uptakes sort of by mid-century. And they also have this warming making carbon losses, which means that those flatten out or start to decline over time. And we really don't know. So we really have lots of questions. And one of the major uncertainties in telling whether these models are correct or not is whether or not they get the timescales right of carbon cycling. So that's where we've put our effort, is to use a clock to try to say, okay, the models are predicting certain timescales of response. How realistic are they? And so that's where a lot of my work has gone. And there are two ways you can use radiocarbon. So we're all familiar, I think, with the use of radiocarbon as a dating tool. And that relies, so you need, nuclear reactions require very high energies. And so the high energies that make carbon-14 largely come from cosmic rays, these galactic cosmic rays. They interact with nitrogen atoms and oxygen atoms in the high atmosphere, and they can make a carbon-14 nucleus from a nitrogen-14 nucleus. It's unstable once it's made, and it will decay back to a nitrogen-14, but it takes about 6,000 years on average for that to happen. So we have carbon-14 naturally in the environment because it's created constantly and it decays relatively slowly. So with dating, the carbon-14 in the atmosphere becomes CO2, gets taken up by plants, goes into living organisms, and once they die, the carbon-14 can decay away, and we can figure out how much decay has taken place, and we know how old it is. That's the basis of radiocarbon dating. So if you look at soil carbon, so there's a lot of concern about soil carbon, and what we've been recently able to do is put together all of the soil carbon measurements that have been made over the years of radiocarbon. So we have this ISRAD, this is our International Soil Radiocarbon Database that we've put together. The dots show you where all the published data are for soil profiles of radiocarbon. And what we've done is just said, okay, what's the mean age of that carbon using this radioactive decay? And the histogram on the right shows you sort of a machine language informed mapping of those sites to the globe. And the blue part, it's how much carbon total it has what age. And you can see there's a skew towards the right. The very old ages are mostly these far northern permafrost kind of areas. The areas more towards the left are the tropical areas. The top soils are younger than deeper soils, but of all of the carbon, if you add it all up, only the very leftmost, the topsoil, about 450 petagrams of carbon, is cycling on timescales of 1,000 years or less. So we don't have to worry about most of that carbon in soils because it's not going to react on timescales that we care about. So we need another tool. Let's see. Ooh. I thought I had another slide there. I guess I don't. So the other tool that we have is bomb radiocarbon. And that's the carbon-14 that was created by nuclear weapons testing in the 1960s. And let me just see if that slide is here somewhere. Oh, here we go. So that allows us to track carbon on shorter timescales through ecosystems. So it's a nuclear reactions, we have high energy, but it was only for a specific period of time, but we approximately doubled the number of radiocarbon atoms in the atmosphere in the period of a few years. So it's kind of a tracer that we can use to follow the carbon flow through ecosystems. And that's pretty much what we do here. If we think about how carbon flows through ecosystems, forward. It's fixed by photosynthesis. Then the products of photosynthesis, those sugars, are allocated either to leaves, stems, or roots. It can be respired to support the metabolism of the plant or to support growth of tissues, or it can be used to grow tissues. And those tissues will stay for a few months for leaves, a few years for roots, and maybe a century for the stem. Those dead tissues then enter the soil where they are subject to the microbial community, and they are returned to the atmosphere as CO2 through decomposition. And that very small amount gets stabilized in soil organic matter, and that's the part that stays around for thousands of years. But most of it is cycling much faster. And so that's the part that we want to study. We also have shortcuts like fire. So if we look at a histogram, or a PDF of how much carbon gets respired and how long since it was fixed, we can see there's kind of a distribution there with plant respiration being faster than what goes through the decomposition cycle. And that's what we use the bomb C14 for. So this is a graph of carbon-14 levels over time. I just want you to look first at the black curve, which is the atmospheric levels. And those were measured in the atmosphere as all this has been happening by a number of groups. The units aren't so important, but the peak in about 1964 was the peak of all radioactive production. There were a lot of isotopes produced in these nuclear weapons tests above ground, and because of them and health concerns related to those, they stopped in 1964 with the moratorium on testing. And since then, the radiocarbon levels in the atmosphere have dropped by a known amount every year because we measure it. And that's as that carbon-14 is taken up by the oceans and taken up on land and diluted by fossil fuel burning, which has no carbon-14 in it. So the point is that any plant fixing carbon in any year will have a specified radiocarbon signature that's special to that year. So if you look at the small box now, maybe in 2008, we could measure respired carbon. The fixed carbon would follow where the black arrow is. When we measure respired carbon, it always has higher carbon-14 than the atmosphere that year. So what's being fixed by the plants is lower in C14 than what's being respired. And that's a measure of how long ago, on average, that carbon was fixed from the atmosphere. So this is our time lag. This is what I call the transit time for carbon to transit ecosystems. And we can quantify it. And so this is an example of quantifying that for a tropical forest in the central Amazon. We had to do a lot more measurements than just carbon-14. We have to quantify the fluxes of CO2 from each of these processes. We have to model the wood pool because we can measure certain amounts, but we can't always measure everything. And but the point here is that a lot of the carbon comes out rapidly through plant respiration. In these forests, the big surprise was that very little of it is actually used to grow tissues. Only about 25% of what gets fixed makes wood, whereas in a temperate forest, about 50% is used to make wood. So already that was an assumption that was being used for tropical forests that wasn't true. And if you add it all together, we get something like a 5 to 12 years lag time on average, but that average is a lot of fast carbon and a less, much slower carbon. So what can you do with that? You can say, okay, we have these models that have CO2 fertilization, so let's see if we increase the inputs to such a system, how it will take a certain amount of time for the outputs to increase to match those increased inputs. That's the lag time. And during that period, you can store carbon. So how much carbon can we store over this period where CO2 levels have increased? And we have to have a sensitivity factor there. That's something that we can argue about. But basically, that's a very sensitive factor. We're saying production now is 20% higher than it was pre-industrially, which is a lot. And even then, we don't come up with the basin scale estimates for the Amazon of how much carbon is being stored. So my argument would be that this process is not the one it can't be the one that's responsible for the uptake we see in the tropics. There must be another process. Either we're not accounting for regrowth of forests as well as we think we are with satellite information, or there's another process at work that we haven't counted on. So just going back to our mess of our understanding right now, our estimates probably are not very realistic. These models that use large carbon storage due to CO2 fertilization are overly optimistic. And so we need to rethink things a little bit. And probably we're more likely to be flat and losing carbon than we are to store as much carbon as they're predicting. So I want to switch gears a little bit. So one of the things we decided was maybe soils aren't so interesting after all, because a lot of the carbon, there's just not that much carbon in play compared to the amount that's in forests. And forests have carbon that takes centuries to grow, and it's a lot of carbon. It's about 700 petagrams of carbon, more than in this active pool in the soils. And one of the observations is that a lot of older trees are dying. I think anybody who lives in Europe recognizes this, that with some of the droughts, we've had massive die-off. It's usually insects that kill off the tree, but we don't really understand what it is that makes trees die. Is it old age? Is it drought? Is it something else? And so we've recently started to look at this, especially in tropical forests, where the trees are big, they are old. The Amazon has about a seventh of all of the wood in the world that remains, and it takes decades to centuries to replace once it's killed off. So one of the things we've looked at is let's try to kill a tree. So one way to kill a tree is to prevent its carbon from getting from the leaves to the other parts of the plants, and you do this by what's called girdling. You cut the phloem, which is the tissues that do that transport. And then we've been looking at the respired CO2 to see what the trees do to survive. So on the graph there, the black points are showing you the carbon-14 content that's being respired by normal trees that are uncut, and it pretty much matches the atmosphere, so they're respiring things relatively quickly. The red curve is showing you the increased C14 in the girdled plants. So they're using older and older carbon reserves up to about 15 years old, but they're taking about a year to die before they exhaust those reserves. So it's just a hint that we're trying to explore how resilient these trees are, how their stores keep them alive. Just because we're in Italy, this is a study where we didn't girdle the trees, it wasn't experimental. There was a late frost, and basically we saw similar things happening. The older reserves were used to regrow the leaves that were lost in a late spring frost. Okay, so I'm going to run out of time here, but I want to just very quickly introduce our Balzan project, which we're calling Carbon and Water Cycling in a Changing Amazon, and that's following up on some of these things. It's especially a collaboration with Paulo Brando, who is both at the Instituto de Pesquisa Ambiental na Amazônia, IPAM, which is an NGO in Brazil, and he's also a professor at University of California, Irvine. And it's it's a region of Brazil in the arc of deforestation. So one of the big questions is, as the temperature warms, what will happen to the remaining forests there? It's heating faster than the rest of the land, partly because of the land use change. And these forests are really just remnants, and they're degrading quickly, and we want to understand they're more susceptible to fire and other things. And so what's the future of that? It's already this is what it looks like when you fly in from above. It looks like a very agricultural area, and the warming comes from the differences in evaporation between the vegetated surface and the unvegetated surface during the dry season. And this is a satellite image that shows you the surface temperature. The soy field, which has no soy in the dry season, is at 55 degrees centigrade, or 50 degrees centigrade. It's 20 degrees cooler over the forest. And if you look regionally, that's what's happening here. The blue area in the center is the Xingu Indigenous Reserve, and all the areas around it have been partially deforested and they're warmer. So just very quickly, our goals are to assess this idea of the tipping point for Amazonia. Are we going to go to a novel vegetation type that's more savanna-like? Which trees are going to survive, which are going to die, and what does that have to do with their carbon reserves? And so this is our question, will we end up in a new stable state, or will we have resilience and go back as the temperatures continue to warm and there are more and more disturbances? What are the consequences for biodiversity? And this is just to show you, there's an experimental site there where they've been burning, and starting in 2003, the forest looked like the top, and now it looks like the bottom. So this is the question, is it going to recover, or is it going to keep degrading? And these are a few of the people that we're supporting, and it's a large group working there together, and I'm very happy to be able to use the Balzan funds to continue that work. So, and thanks to all of you for your attention and all the people who helped me through my career. Thank you.
Thank you for this very beautiful talk. And I wonder if there are a few questions. We have time for that. Please.
Answer with your technology. People tend to focus on limiting the increase in global warming. Let's say 1.5 degree or whatever people can agree on in Glasgow or anywhere else. One may doubt if you can reach that relatively low level, but few people seem to consider. I don't think it works so well. I actually prefer without this. You can hear me. No? Okay. So in the unlikely event that we, let's say, in 10 years' time, we are able to reach 0 new emissions. Unlikely to happen, but just take it as an academic experiment. How long time would we need? How many 100,000 years do we need to live humanity with this elevated level of carbon at that point in time? Because already now, and even worse when we reach 1.5 degrees, there are severe consequences all over the world. One of them is that hundreds of millions of people will lack water, lack fresh water. So when can we return to the good old days when it comes to the CO2 level? How will the flux reduce the excess carbon in the atmosphere?
So, I don't know.
Yes.
Okay, so that's probably too much to answer in a short period of time, but The good news is that there's more, there's sort of the carbon function of forests and there's the climate function. So in this region, deforestation causes the temperature change near Mato Grosso in the regions outside the Xingu forest is 2.5 degrees warmer than pre-1970 during the dry season. So it's already one of these places where it may be hard for humans to survive the excess heat during certain dry season days. And it may become uninhabitable, you know, if you look at the projections. The good news is that that's reversible very fast. So even these degraded forests, they evaporate as much water as the relatively controlled forests, undisturbed ones. So if what you want is, we can manage certain parts well to reduce the excess heat. And that's one of the things the farmers there are actually interested in because their soy crop is starting to suffer because of the high temperatures. In terms of the excess CO2, how long it's going to stay in the atmosphere, that is why people are looking at forestry options to you know, pull things back out. But those processes, I mean, you can't grow a tree, you can grow a tree slowly, but you can burn it in a day. So, so we need to not just, you know, count on trees to sort of help pull the carbon back out of the atmosphere, but also to prevent deforestation, because that's a large part of our emissions that we could do something about right away. So the rest of the CO2, we will be stuck with it for a while because you know, there's a limit to the rate at which the ocean will dissolve it, and you know, geology ultimately will determine it. So we're stuck with at least 15% of what's in the atmosphere now for 10,000 years. But in the shorter term, there are things we can do to reduce, and you know, maybe some of the engineering solutions will have to be part of that. Okay.
Sild?
Yeah, thanks a lot, Susan, for a very clear presentation. As you clearly put forward also yesterday, reducing the carbon dioxide level is a race against the clock. In that context, I would like to ask you, what do you see as the main obstacles or challenges in the research itself to come forward, let's say, with further guidelines in terms of what is the most optimal process to go also towards the politicians, for example? Because there are a number of intrinsic uncertainties. You explained that in terms of this fertilization. And of course, we could ask you, can you speculate a little bit? What are the missing processes? But what do you see in terms of where should we really focus on in terms of advancing the science itself?
If I really want to solve the problem, I mean, so what we can do with degraded lands is we can put back the carbon that was there before. There's a lot of hope about things like biochar, you know, putting inert things in soils. I think there's a lot we can do with wood products to make sure that they're not decomposing right away. But you know, what the biosphere can do is limited. I think some of these, I think we're gonna have to remove CO2 from the atmosphere and pay to do it rather than hoping plants will do it for free. I mean, some of the reforestation, like the Chinese large Kyoto forests that were planted, they are big carbon sinks, but those trees are getting older now, and they're storing less carbon because they're not growing as fast as they mature. So we have to then do something with those wood products to keep them from going in the atmosphere. There's lots of ways to do that with building materials, but it's, you know, again, forcing humans to change rapidly, which is not something they're very good at. So.
Perhaps I have a question myself, if you allow me. We hear many times speaking about carbon deposit In other words, burning fuel, but deposit the carbon somewhere
Yeah.
where it does not go into the atmosphere. What is your opinion about this possibility? How
Yeah.
realistic is that?
Well, I think it's realistic in some places, right? So there's the new Iceland plant that just went online that's capturing and sequestering CO2. I think those technologies are developing very rapidly, and I think there's lots of reason to put some hope there, and that we can put those first at these point sources where there are huge emissions. I think the ones that are, trying to capture just from the background atmosphere, carbon dioxide is very low concentration in general, so it's harder to do those. But I think there's a lot of hope for those technologies in terms of reducing emissions. Yeah.
Okay, thank you very much. We are not late, so we have time for a more quiet presentation. And the next speaker is Carlo Vis, who's going to introduce the prize winner, Jean-Marie Tarascon. Please.
Thank you, Mr. Chairman. Good morning to everybody. I have the honor and the pleasure to introduce to you Professor Jean-Marie Tarascon. He was born in Meillan-sur-Garonne in France, and he's since 2014 professor at Collège de France, holding the chair of solid-state chemistry and energy. He was elected member of the Académie des Sciences in 2004. He began his academic career at Bordeaux University with a master's degree in chemical engineering, followed by a PhD thesis in science in 1981. Jean-Marie Tarascon moved then in the same year to the United States at the Cornell University with a postdoc contract to study superconducting materials at higher critical temperature. 1 year later, he joined the Bell Laboratories, the holy grail of scientific research. In 1983, he moved to Belcore, the Bell Lab subsidiary devoted to telecommunication, working initially still on high-temperature superconductivity and then on energy storage. From 1990 to 1994, he directed a research team centered on the conversion and storage of energy. He went then back to France as professor of chemistry at the Jules Verne Picardie University in Amiens. There he directed as well until 2008 the Laboratory of Reactivity and Solid Chemistry, and until 2010 the European Network of Excellence, Alistor, that he created in 2003. Alistor currently federates 19 institutions performing cross-cutting high-level research in the field of batteries and their materials. Professor Tarascon created then in 2011 the Network of Electrochemical Storage Energy, a research federation by CNRS, involving some 20 academics and 17 industrial partners in the field of batteries and supercapacitors. Rechargeable electrochemical batteries, as one of the most versatile energy storage technologies, play a central role in the ongoing transition from fossil fuels to renewable energy for achieving a greener planet. Jean-Marie Tarascon's brilliant fundamental research on materials for electrodes and electrolytes applied to industrial technology has led to the global availability of safer and more efficient lithium-ion batteries. And reducing the environmental impact through better choice of materials and synthesis method, as well as improving battery lifespan and easing their recycling, have always been among the principal objectives of Professor Tarascon. His contribution to electrochemical energy storage alone encompassed nearly 500 publications and 100 patents about. So I would not go into detailed description of the scientific achievement, but will nevertheless recall some major breakthrough. During his time in the United States, he identified in 1993 a specific electrolyte composition that remains nowadays one of the most popular electrolytes. In 1994, he created a plastic lithium battery based on a polymeric system which is thermofusible, mechanical, robust, leading to the first commercial plastic batteries made to custom dimensions, fitting the user's needs for hybrid vehicles, telecommunication, instrumentation, and so on. And this technology has been licensed to more than 25 manufacturers nowadays. In Amiens, Jean-Marie Tarascon and his colleague demonstrated that through mechanosynthetic processes, the electrocapacitive properties of carbon electrode towards lithium can be doubled. And another major breakthrough was the discovery and study of an entirely new family of organic molecules to make renewable and easy recyclable electrodes. Further, Jean-Marie Tarascon, with his new group at Collège de France, was able to explain the surprising energy accumulation capacity of certain classes of oxide, starting with the little-known role of negative ions in reduction-oxidation reaction. And this discovery has opened up a vast new field of research on novel materials for energy storage and water splitting as well. Professor Tarascon played then a major role in the development in Europe of sodium-ion batteries as a cheap and sustainable alternative for lithium-ion, working on fundamentals and technology. He's at present very involved in the development of sensors integrated into batteries to understand in situ chemical evolution, optimize functionality, and extend lifespan, so reducing again the environmental impact. In addition, over the course of his career, he has trained a large number of PhD students and researchers and has initiated important international networks devoted to electrochemistry. So by now, I'm eager as you to listen and enjoy the presentation of Professor Tarascon. Thank you for your attention.
So good morning, everyone. Thanks, Carlos, for this nice presentation. And of course, thanks to the Presidentes for also this Balzan Prize. That is really an honor. So today, of course, I'm not going to go to my life, but I'd rather like to discuss with you the excitement that is going on in the field and the research that I am doing on the field of batteries, where I entitled Smarter Batteries Based on New Embedded Sensor and Life Monitoring. So I want to give you the presentation in order to stress the science and the innovation going behind the development of batteries. And you are going to attend this talk, you are going to see some kind of material research, you are going to have some physics research, and I will end up in some supramolecular chemistry in order to give you more or less kind of nice overage of what's going on. But of course, before to do this, I would like to remind you, or at least the status of battery research today, and maybe also tie this presentation to the previous speaker and also to the next one in order to show that more or less all these three prizes are well interconnected. Indeed, why are we bothering with batteries and what is the contest? And we are always targeting the CO2 consumption and try to diminish the CO2 consumption. So of course, there is a great amount of hopes that is placed and moving from fossil fuel to renewable energies. And when you are thinking about renewable energies, you know that they are quite abundant. And indeed, if you can really look at the sun can produce 10,000 times the energy that we need on Earth in the case. And the price has been going down. However, there is a main issue. All these kind of renewable energies are a flux energy, rather than stock like fossil fuels. So automatically, you have a problem of intermittency. As you see here, if you look at the peak power of a photovoltaic farm, it's not flat. So you need to more or less average this fluctuation. To do so, we are going to do it by using electrochemical storage. What is electrochemical storage? Is nothing else than the conversion of energy of a bond into electricity, because both contain electrons. And what is the device that is doing this? The device is the famous batteries. So the type of batteries that we are using for 200 years, more or less, have been on the same process. And this is more or less why the type of batteries that all of you have today and your laptop and so on. This is the famous lithium-ion batteries that is based on two inorganic compounds that are full of vacancy to uptake lithium and to release it. And here, what you are doing, you are looking at the potential of voltage versus capacity. And what is very important for you is the surface area between this curve. And this is giving you the energy density or the autonomy or the time that you will have to talk at your phone. And what you are looking at is a very simple classical terms, very simple equation, in which we are using energy density, which is a voltage that depends on, as you can see here, the difference of electronic structure of the materials and also of the number of holes. So this is more or less, I give you this because this could be useful later on to understand this presentation. So now, what is happening in the field? We have done quite a large amount of research. People have got a Nobel Prize for this technology. But I think, one person that also deserves a great credit is Elon Musk. Because it is because of this person, or 5 years ago, that the field totally blew up. Means Elon Musk wants to give energy to everyone in the world at a large scale and low cost. The result, the price of the lithium ion has been decreasing by a factor 10 over the last 10 years. At the same time, and you are aware that in Europe, people are building gigafactories like mushroom. As you can see here, more than 20 gigafactories are growing. Why? Because Europe wants to be really a big player into this kind of very lucrative market. So as you can see here, we are going to shoot for about 16, 17 gigawatt hours of energy storage by 2030. But if you look at this kind of stuff, Europe wants to increase by now from 1%, where we don't really exist, as a matter of fact, to about 19% in 2029. So this is nice, but you need to keep in mind that if you do this, you will need to have 2.2 million tons of materials, cathode, and 2.2 million tons of lithium. And by now, Europe is importing 98% of the raw materials. And I think this will tie to the third Balzan winner. We'll talk about resource. So now, what I would like to do, this is more or less where research is today. Now, where we are going to go. And this is more or less what you are going to see, what is more or less my Balzan research. You have now all these kind of vehicles that are growing. You have more than 400 type of vehicles. The sales will be 150 million in 2040. And of course, if you look at renewable energy, also you can see the numbers are staggering. So this clearly indicates that we have, in this case, huge performances, but we have a cost production evolution and everything. And the question is more or less how this impact research tomorrow. And this is more or less where I am going to start the science innovation. I think you have two types of main school in our field of research. Either you look for new systems, new technology for the 20, 30 years, or, as you will see later. So we look at this new technology, and as a matter of fact, this is air that we are just come out with sodium-ion technology now that is kind of, I will say, helping considerably the lithium-ion technology, and of course, sodium is quite more abundant. But the point that I want to discuss today is this part. It's more or less, we have this kind of lithium-ion technology, and the question is how you want to improve it, because we are going to have this technology everywhere, and we need to increase its reliability. And this is more or less what we are going to look at it. Now, if you look at this technology, what the main issue here is indicated here. Here you have really all the story that you have in this black box that is the lithium-ion batteries. And issues that we have are here. Means that during cycling, you can have dendrites, you can have cracks, and remember on this, and so on. You have plenty of effects. So what you want to do here is definitively you want to anticipate this kind of battery dysfunction, and but which strategy? And the strategy that we want to develop is really a strategy that you are going to diagnose and localize the issue via some sensor, and then when you localize the issue, you are going to try to develop self-healing processes. So how we are going to do it? And we are going to get a large amount of inspiration from the field of medicine. So what we are going to do, we are going to try now how we can put sensor into this battery. And as you can see, a lot of people in the past have tried to put sensors, but these sensors are really invasive and so on. So what we want to do here is to be smarter and try to use optical fibers. And the optical fibers, here again, is what you are all using, because this is more or less where you transport all your data and telecommunication and so on. But at the same age, or the same area of optical fibers, you have also a huge development of sensors based on optical fibers. And why? Because these optical fibers are very small, insulating, and they are finally ideal for batteries. So what we have decided is really to try to implement this kind of optics into our batteries. So to do so, we are going really to use the basic principle of these optical fibers, and the one that I will describe it, it's relatively simple, is a fiber grating optical fiber. To make the simple things very simple, you take a classical fiber in which we are going to have a sensor here where it is really a periodic change of the refractive index. And to make it very simple, the light is going to arrive, is going to be diffracted on this sensor, and what you are going to look at it here is a reflex spectrum. And we are going to use this kind of spectrum to do our analysis. And as you can see, it's very simple. Now you can see that the gradient is going to be affected by the temperature. So in this case, when you are going to increase the temperature, this resonance spectra is going to change. Now, if you change the pressure, as indicated here, we are also going to have a change directly in this black reflection. So this is more or less the basic principle. Now, how we do this? The advantage here that we are going to take, you see, real battery now, and I'm going to inject my fiber into it. And here you can see the voltage, as I mentioned to you, and now I measure the temperature as along this chemical curve. And I can get large amount of information here. Then I can also measure pressure. I use a fiber, and in blue, you have, in this case, a pressure. And you can see, very interesting, you have the same time, increase of pressure, increase in temperature. This is nothing else than a chemical reaction going on into your system. So doing this, we can now directly access to different characteristics, and we can use now this kind of technology to discover new electrolytes. So if you do this, we can also look at temperatures, and now I know what are the gradient temperature within my battery. Because here, you see I put a sensor at the middle, and I can see the difference between the inside and the outside, and this is very important for the lifetime of your battery. But you can also put several sensors, because you can use optical multiplexing, and in this case, I can have a temperature imaging of my battery. And you can see that, of course, when you use the battery, the connection is more or less quite correspond to the middle and so on. So this is what we can do in terms of physical measurements. Then we want really to know, hey, what's the chemistry going on into this stuff of light box. So we are going there to transfer the heat here into, I will say, the temperature into heat as indicated here. And when we do this now, to make the story short, we can now have access to the type of cascade reaction going on within your battery, and to know really what is happening. So we can play this kind of game, and just to give you an example of what we can achieve is indicated here. This is, for instance, a kind of search for electrolyte discovery, where we are going to add different additives, and what we are measuring here is the overall heat as you can really add different additives. And if you do this, you can have this kind of tables in which we accumulate the heat, and you can find that in the case of number 5, when you have this combination of the synergy between all these different molecules, we have the lowest energy. So mint in this case is the best electrolyte for application. And this is, for instance, how we discover our electrolyte for the sodium-ion batteries. So here, what you have looking here, we have done something, but it's not great because we detect that something going on, but we cannot identify this molecule. So how we do this? We are going to follow in our reasoning, and if we want to do this, we have been using these FDGs, this optical fiber, and which in this case, the fiber is really my waveguide. Now, if I want to have access to the chemistry, I need to have an interaction of the light with the environment. The environment, in this case, will be my electrolyte. To do this, what I need to do is really to put some tilting. And now, if I tilt, as you can see here, my sensor, I am going to have now interference of the light with the surrounding environment. And by doing this now, I can have access to the refractive index of the electrolyte, just to give you more or less what is happening. Now, if I have this refractive index, I can go one step further and understand what is the meaning of all of this. To do so, I have now several reaction mechanisms, And knowing this mechanism, I know what is the refractive index associated to each of these cascade reactions. And if I do so, I can directly, in this case, determine, finally, what is the best way or which process is going to follow. And in this case, you can see that the route number 1, as indicated, is our best process. So by doing this, now, I can follow when a battery is aging over thousands of cycles and know, finally, what is the state of health, of state of charge, and so on. But here again, you can see we have made progress because now I can decouple two mechanisms, but I still not be able to identify the molecule. And here I am going to share some results that have been really obtained through the Balzan prize, how we can really solve these issues. And you are going to see what is happening. So what I want to do now, I really want to test to probe this outside environment. So I want to get this evanescent wave. So here I go back to some basic that you all know, where I look really at the spectra. And you have near infrared, you have the famous SiO2 fiber that we are using for telecommunication that work in the 0 to 2 micron wave range. And now if I want to go into chemistry, I want to go into molecules, I want to look at the vibration, I am obliged to work on the 3 to 13 micro range. And here, I think the first time that we have done this, and I think that everyone has done this, is really to move to this different type of fiber. And what we have decided is to move away from the silicon fiber and to move to chalcogenide fibers as indicated here. And now, I have, in this case, opened my window, and I can really have access. And by doing so, as you can see here, now, I can really look at what's going on into the black box in terms of chemistry and knowing which molecules are popping out as I run my batteries and overcycling and so on. So, and we can go into details and knowing more or less what happened to the different type of carbonyl or carbon-carbon groups, even really looking at some methoxy and so on. So we can really have access to all of this. So this is more or less what we can achieve. And I think this is the first time that this has been done, where we can now understand the the chemistry within the battery, within the black box. So we have done this. Now the question is how we can implement this stuff, and this is here the case where we were able to develop our sodium-ion batteries, and you can see here when we went really from, to a certain extent, an idea, a concept, to a product as indicated here. And nowadays, we are, I will say, developing this sodium-ion technology that is now entering the market in replacement or to help or to diminish the pressure on the lithium-ion batteries. So this is more or less what we are doing. So now the next point I want to talk with you is the type of self-heating. So as I mentioned to you, we have now detect, we can diagnose what is a malfunction of the battery. And like, again, in the field of medicine, if you diagnose a tumor, you try daily to provide a curing. And here we are going to do the same thing. We are going to do now what is happening and how you want to cure. And especially, I mentioned to you, you can have cracks into the electrodes. So here, we get also inspiration from the field of science, from the field of life, where we are, in this case, looking at the cell membrane. And if you look at the cell membrane, more or less what it is a bipedic layer of indicated here, when you have these protein channels, which are really serving as a gate to selectively really trap the different ions, and as a matter of fact, that in this case, can send these kind of special signals that are going to trigger your nervous system and so on. And here, what is very interesting to look at it is the way that this membrane is made. This membrane is made of lipids that are agglomerated at the molecular level by kind of non-van der Waals interactions and reversible. And this is more or less nothing else than the supramolecular chemistry. So here, we are now going to use supramolecular chemistry to design our membrane. And to do so, we are going to use a supramolecular agent that is very well known, biodegradable, that is cyclodestrine. And the cyclodestrine is this kind of 3D tunnel molecules with high polarity that is going to specifically trap different types of anions. And here, for instance, we are trapping this kind of polysulfides. And the advantage, since we are in this type of host-gas interaction, supramolecular interaction, they are reversible. And in the reason why, I can now use this membrane and use temperature as a stimulus to either trap my species or release my species. And doing so, we can also even one step further, and we can use now this kind of supramolecular chemistry to develop kind of very elegant architecture. As an example, we can really use this kind of architecture where, in this case, I am going to thread the cyclodestrine along these PO polymer chains, which is going to be tied really to this PAA. More or less, I am kind of doing molecular necklace of the cyclodestrine. And this enables you to allow some elasticity to your electrode, as indicated here. So if you do this, this is more or less what you can have. You can have now an electrode, as indicated here, in which you have this kind of pulley effect due to this elasticity of this molecular design, and this prevents some cracking into the electrode. And to more or less tie everything together, in order to check if you have cracking, we go back to this kind of optical sensors, and as you can see here, as you can see here, we nicely see now the difference when you have this kind of additives, this kind of nice elastic binder, where you can dissipate strains and so on. So this is more or less what we are doing nowadays. So what finally is the Balzan project, where I am still working, because I think all the work on infrared has been done under this project. This is more or less a dream that we are following now. This is more or less what I want to share you, what the battery should be in the next 10 or 15 years. Where we have today, you know a battery is a plus and minus. In 10, 15 years, I believe that you are going to have an analytical output as clearly indicated here. And then, the Balzan project is going now to integrate all these various sensors in a single fiber in order to diminish the wiring of the system. And having done so, we can then design better battery management systems that are going to be connected to, of course, different algorithms of machine learning and artificial intelligence that are going really to act on the actuator to use, finally, the self-replicating agent as a stimulus. And all of this is going to give you great advantage, because what we want to establish is finally an electronic passport for the batteries in the future. Means that we know more or less what will be the lifetime, what will be the penability of the batteries. And by doing this, we are going to increase the use of the efficient use. We can do some more predictability, multiply the lifetime, enable battery second life, and so on. And all of this will lead to a lower CO2 footprint and the batteries. So this is more or less what is the project about, and I want to thank all the people that have been working on this project. Some of them are already funded by the Balzan Foundation. And I want to thank you again for your attention.
Thank you very much, Professor Tarascon. And now we have time for a few questions or comments. Sir?
Thank you very much for a very fascinating presentation. You mentioned in the beginning the challenge for Europe in terms of importing raw materials. And in this context, it's very clear, let's say, the sense of urgency in this domain. My question concerns the European position in the research itself. Of course, there is a global competition. Where do we stand in Europe? Also, let's say, in the content of the priorities given to this domain by the European Commission in our research in this domain versus the competition, let's say, in, for example, the US or Korea or Japan or China.
Okay, I think a very good point. I think in terms of competition, I think at the scientific level, I think in all modesty, Europe is at the same level that China or the States. I think where we are not good is the commercialization. Is the commercialization, and I just give an example. I mentioned to you about the sodium-ion batteries that has been developed in Europe and France. And we are, unfortunately now, again, we kind of betray, history. We are obliged to subcontract this to China to make this type of device that I mentioned to you. So I think this is the main difficulty that we have today. And in terms of these gigafactories that I mentioned about 20, 22 gigafactories. 12 of them are really sponsored by Asian companies. So more or less, by trying to enlarge the European sovereignty, we are really facilitating the development of battery manufacturing in Europe as well. So I think, we have always this issue where to commercialize and how can we make Europe more efficient and to commercialization. I think this is the main issue. We have this in batteries, we have this in photovoltaics, and I think we found this in several research fields.
Thank you. And are there other questions?
Well, it was truly fascinating to follow your ideas for creating a quantum leap in battery technologies by combining expertise in chemistry, fiber optics, and biological elements. So we can all hope in this room that you will eventually succeed, and if the Balzan Prize somehow can add its contribution to this success, we will all be terribly pleased. Well, your lecture is 1 out of 2 under the headline Environmental Challenges. We will have a presentation by the humanities sections after yours and a discussion after that. So I just wonder, if you solve this particular problem, if you have success, this should be shared with the world in order to reduce the environmental impact of the human race. However, we are seeing new walls being built. We are not anymore a global society, we are becoming insular societies. Walls around China, walls around the United States, walls around US, and probably one day also around India. What is your view? Do you think your research will be impacted by this, as battery technology is becoming a geopolitical asset?
Okay, I will try to answer your question that is relatively broad. First, I should mention, why this type of futuristic research? Because this is a kind of discussion that I have at the European level to a certain extent. If you want to be back in the scene of competition on batteries, I think we lost the battle on the classical lithium-ion. And I think you need to look ahead and what will be the added value. Okay? Now, if you look more or less what the added value, what is needed tomorrow. I think tomorrow you are going to have batteries and all the gadgets, and even then electric vehicles, you are going to put back, electricity or energy into the grid and so on. So you need to have extreme reliability. So we need to have this type of sensing and so on. So what I am looking more or less is kind of breakthrough into the field and to take ahead, scientifically speaking, against other kind of countries. And here I think we can have the product with added value that will, of course, will spread throughout the world. So I am really optimistic for this kind of breakthrough and sensing to bring added value to our society. And because it's needed, tomorrow we need to have this kind of very high accuracy and controlling the way we are managing energy. And I think this is a way to do it. Then in this kind of, topic and this kind of research, I think there are 2 parts. The first part on diagnostic, I think for me is we just need to transfer, we have the fundamentals. The part on self-healing and so on is more critical. But I think that this has a tremendous potential to have a large impact and whatever in China and so on. Because, by the way, this type of projects are done in collaboration, one of it with the University of Hong Kong, as a matter of fact, and some Chinese companies are moving very strongly in this stuff also. So I don't know if I answer your questions, but we can talk.
Thank you. Please.
Thank you very much for a fascinating talk. Looking ahead, when your vision is actually implemented and we have batteries in electric cars, most vehicles are electric cars, could you say a little bit about the infrastructure that one will need in order to be able to service these batteries and to be able to take the diagnostics that you have described and to make certain that electric vehicle batteries can be maintained, and what that will mean for the whole infrastructure that we have? For example, in EVs at the moment, we have mechanics who are used to the internal combustion engine who will have to be retrained to understand battery technology. Could you speculate about the structural changes that will be needed going ahead?
Okay. Now, very good point. And I think your question I will try to answer in two parts. The first one is more or less you talk about batteries, about electric vehicles. Here you are touching an issue that I haven't talked today, which is more or less the charging time. And the charging time is what is relatively limiting now the application. And it's why nowadays we cannot charge a battery in less than 10 minutes. Doesn't matter what you look in the newspaper and media. This is totally impossible. The physics say no. Simple. So you can have really in the highway, I will say, more rechargeable stations. Okay. Now, going back to your very interesting question that we are, of course, thinking at the same time, how we are going to implement this technology and what change will be making. Of course, if I would have introduced optical fiber 10 years ago, you could have told me you are crazy. Nowadays, if you look at Tesla car, there is already an optical platform on the Tesla vehicle. So it means that we can really integrate this kind of sensor into the optical platforms that does exist. And then, maybe I bring you too much in the future about this kind of technology, but I think it's not the sensor that are not the issue. The question you may ask is, I try to enhance the lifetime of the battery for more than 10, 20 years. But the question that I have to ask, and we are looking at it, will this sensor will last longer than the batteries? And here, we are working this kind of electrolyte, this kind of nasty chemistry. And this is more or less the kind of issue that we have it. And then, of course, you want the elite for detection. Detection, when we are doing at the lab, we are scanning the frequency. Now, you really want to put in practical, we need to have a digital system, or digital, where in this case you will scale a wavelength, and you will have a yes or no. I have to act. So we are looking into this kind of stuff. But again, I want to mention that this is not a pipeline dreams, because we have already achieved some of the sensors and so on, and we have them here. And also, if you look for people who know optics, all these sensors that I mentioned to you are used commonly in the world. People are doing health monitoring of structure, airplane, and so on. Use either this optical or acoustic sensor. And we have to learn of it. And the difficulty is how you are going to merge these two types of communities in order to develop all together this type of sensor and for implementation. And it's what I try to do now, to try to bring this community together and learn a lot from the other people that are using this stuff commonly.
Okay, thank you very much. If there are, yes, I see one question over there.
You already mentioned the electric vehicle producing companies and the gigafactories. How much are you already connected with the real economy? They should be all over you, getting your research, because the quality of the batteries are key for them to succeed in the future. And we hear that Tesla is in the lead at the moment. So maybe two questions. How much are you involved already with these companies, or how much they try to get your research? That's the first question. And the second question, could you give me or give us a view who is really in the lead regarding the batteries at the moment?
Okay. In terms of research, of course, we have, I am taking care of the French network, and we have automatically contact with all the French EV makers and so on. And we have also contact at the European level. It's one why I think, and the battery research today is highly financed, more or less. Now, who is the lead? I think definitively, well, in terms of research, more or less, as I mentioned to you before, I think Europe is well positioned. In terms of manufacturing, and nowadays, I think Tesla is really getting ahead, because they are the first one, as a matter of fact, that move to this kind of next generation of putting some added value to batteries by doing all type of sensing and so on. Because if you look at the Tesla car, there is a plenty, everything is automatic. And tomorrow, when you are going to have a connected cars, sensing is mandatory. So people are really, all these visionary people from Tesla and so on, have really integrated this kind of stuff and so on. But in Israel, while we are working on this kind of stuff, and our European level, I should confess that the people have more difficulty to bring themselves to the future and to be so risky in this kind of adventure.
Okay, thank you again. I don't see any other question. We are in a good time. I think we can now go to the coffee break, and I would propose to reconvene at 11:15. Thank you very much.
Well, I think we can continue. Suzanne? I have to wait for Tremont. Oui. Well, welcome back. We'll continue the extremely coherent panel of the 2020 Balzan Prize winners. This coherence is due in part to the decision we took in the General Prize Committee to award for the first time a joint prize entitled Environmental Challenges. Before the coffee break, we just heard Jean-Marie Tarascon as the scientists' part of the common prize. Joan Martinez Alier, I have now the pleasure and the honor to chair, represents the responses to environmental challenges in the field of social sciences and the humanities. Donatella Della Porta is going to introduce Joan Martinez Alier. Thank you, Donatella.
Good morning, and thank you to all the participants to this encounter. When I was asked to act as a chair for the Prize on Environmental Challenges in the Humanities in the novel coordinated prize scheme, I have to confess that I felt rather overwhelmed by this responsibility, giving on the one hand the high social and political relevance of the topic, but also the highly interdisciplinary or transdisciplinary characteristics of the field. As for the former, the pandemic we are living in is further highlighting, as well as worsening, the risks connected with a growth that takes no responsibility for the preservation of our environment. As for the fields of studies in the social sciences and in the natural sciences, I think there has rarely been a discipline, a field of study that has been as connected, as interdisciplinary, almost by necessity, as it is on this topic. Reading the list of the nominations, I've been then extremely pleased to see that we had indeed, among many excellent scholars, the nomination of Joan Martinez Alier, not only an eminent scholar, but also a scholar with a profile that perfectly fit all the criteria we had in mind for this prize. First of all, Juan Martinez Alier has extremely broad international experiences, addressing global concerns through a path-breaking work that has and will have an international resonance. A Catalan scholar, Joan has been a deep-rooted cosmopolitan. After graduating in economics from the University of Barcelona in 1961, Joan Martinez Alier continued his studies at the St. Anthony College in Oxford, Stanford University and the Universidad Autónoma de Barcelona, where he became full professor in the Department of Economics and Economic History, and is now emeritus professor in the Institute of Environmental Science and Technology. He has been a member of the Scientific Committee of the European Environmental Agency, as well as a visiting scholar at many prestigious universities. What is more, throughout his career, he has contributed comparative knowledge at a global level on environmental challenges and potential solutions to them, and in doing so, he has bridged different national and regional scholarly traditions in an exceptionally fruitful way. Second, Jean Martinez Allier has been a pioneer in developing a novel approach to ecological issues, a most important concern for our life, within a discipline that has not always valued involvement with real social and political problems. With his ecological economy, he has looked at problems, but also at solutions, at the characteristics of conflicts, and at the moral claims they articulate. One of the founders and later president of the International Society for Ecological Economics, is widely recognized as one of the most authoritative scholars in the environmental studies. Jean has made the fundamental contributions to establishing economics as a field of study devoted to regulating economic activities in a way that promotes human well-being, sustainability, and justice. In several books and articles, he has analyzed the relationships between ecological economics and political ecology, as well as the role played by environmental justice. Most importantly, his approach to environmental conflicts is based on the notions of ecological unequal trade that has profound impact in the disciplines. Among his numerous and important publications, one of the most influential is the volume The Environmentalism of the Poor, that is based on Jean's experiences in researching in all over the world, from India to Latin America. Here, as in other publications, Jean Martinez Allier has made an outstanding, original, and important contribution to the understanding of ecological distributional conflicts. It has been in recognition of these contributions to innovating economic studies that he was awarded the prestigious Leontief Prize for Advancing the Frontiers of Economic Thought in 2017. The prize was assigned for the groundbreaking theoretical and applied contributions integrating ecological approaches with developmental and justice-oriented ones. Third, Jean Martinez Allier is a truly interdisciplinary scholar. Moving from within the social sciences, his work has bridged different theories and approaches within economics and political science with those in the humanities and in the natural sciences. As a highly respected economist, Jean Martinez Allier has devoted his entire scholarship life to developing a transdisciplinary theories of environmental challenges, making use of insights and informations from the natural as well as the social and the human sciences. Fourth, Jean Martinez Allier is an engaged citizen of the world, making science useful in order to address social challenges. He has been extremely active in the dissemination of research results and in the promotion of environmental justice. In particular, through his research, he has anticipated the public outrage emerging on climate change. He studied the challenges for the climate justice in depth, warning about their unequal distributions and the heavy cost that also renewable energies may have in the global south, where lithium and other necessary materials are extracted, but also in the global north with the use of land. The Atlas of Environmental Justice Conflicts, ECODIRECTS, is a precious ongoing collection of information on thousands of cases from all over the world testifying of people suffering from the exploitation of the environment, but also of people resisting it, mobilizing in protest, constructing alternative knowledge, concretely engaging with the protection of nature. This unique open access database on the main ecological conflicts and their cultural expressions constitutes a highly useful source for scholars in several disciplines, as well as for practitioners in the field. Last but not least, Joan Martinez-Allier is a generous mentor who has been able to build a large community of young and less young excellent scholars coming from literally any corner of the world, not only the North and the West, but also the East and the South. With this energy, commitment, curiosity, he has in fact contributed to form several generations of researchers who are helping us addressing environmental challenges, being for them a role model, but also a friend. All of these are important reasons for me and the Balzan Foundations to be extremely pleased and proud to be able to celebrate the awarding of the prestigious prize to John, and grateful that the prize can contribute to further develop his research on climate justice and to the Atlas on environmental conflicts as a precious resource for all of us. Thank you, Jean. I'm so glad.
Thank you, Donatella, for your introduction. And Joan Martinez-Allier, we are glad to have you amongst us and to listen to you.
So thank you very much for these generous words, and thank you for the prize, the Balzan Prize, which I've got, as the rest of the people got the prize, is good for myself, but also for the group, the collaborators I have, which of course are growing in number, because this atlas is a very laborious kind of enterprise. Also, I am very pleased to be here in the Lincei Academy. In the morning, while we were waiting, I read most of this leaflet by Alberto Quadrio-Curcio, and I am very impressed to be here, and thank you. And thank you, of course, to the Balzan Foundation. So I'll go on to my presentation, which is not what is outside, which is a speech I wrote about 1 year ago, isn't it? So I thought I would present something which I just published in the last 3 weeks, and which is linked very much to the issue of climate change. Because I'm going to talk this about LFFU movements, means leave fossil fuels underground. So in my talk, I'll talk about the Killing Card, which already appeared, and then the atlas, and then also about these movements. And then I'll do like an estimate, what in the US they call a ballpark estimate. I don't know why a ballpark, but I mean a very wide estimate of the amount of carbon which is left in the ground through these movements around the world in which people manage to leave coal or oil or gas under the ground. So first this that we already saw, and I think it's slightly exponential, this curve, which is very, really alarming. But even if it is linear, the question, since I started to do this, because I am a lapsed economist, I say sometimes, an agricultural economist, but then I got into environmental issues already in the late 70s, and then in the 80s, and then through a lot of Swedish influence, Anne-Marie Jansson, and also people who had studied with Howard Odum as systems ecologist. So I learned about climate change and what Arrhenius had written already in 1896 about the increase in the carbon dioxide content in the atmosphere, how this would increase the temperature, more or less with the same figures as we say today, 2 degrees, tripling, not doubling, and tripling what would happen with the temperature. Of course, we know much more about the details of this, but this is known since such a long time ago. And the killing curve, for those who haven't seen it, there will be very few here who have not seen this before, shows how since 92, which is when I really started to get into this at the time of the Rio de Janeiro conference, we were at 360 parts per million, and now we are reaching 420 parts per million. And I think nobody is going to stop this until at least 450 in the lifetimes of many of the younger people here, in less than 30 years, I think. So this is, I think that in terms of climate justice, one could say that there is an unacknowledged climate debt or ecological debt from the north to the south. Apparently, there are few people, some scholarly work has been done on this. At the more political or social level, there is a famous citizen of Rome, which is the Pope, who in his encyclical, which is called Laudato Si, in paragraph 51, he describes, of course, it must be second-hand, isn't it? But he describes not only climate change, but also this ecological debt from the north to the south, from the industrial, from the rich in the world, actually, whether they live in the south or in the north. Those of us who have produced an excessive amount of carbon dioxide already, we have to the rest of the human beings, but also the non-human beings in the world. This is not acknowledged in the Paris Agreement, for instance, where there is a clause, explicit clause, and this agreement does not imply any environmental liability in law, isn't it? Because the US and the European Union said, if we accept liability, then we'll get lots of judicial proceedings, international ones in The Hague, perhaps, and we don't want this, and therefore this clause was imposed to everybody. Well, this is part of the argument that there is environmental injustices at a local level or global level, and this is what we try to find out, mostly at the local level, in this atlas of environmental justice conflicts, as Donatella Della Porta just mentioned. All the little points, they have a different color depending on the type of conflict, whether it's mining, metal mining, or fossil fuels, or biomass conflicts. We have 10 main categories, and you can go into this, and you can look at the recent arrivals. And of course, this is a very laborious thing that has been going on for 10 years now. And people use this, journalists use this, and young people doing master thesis, doctoral thesis use this. And we also use this for our own academic work. And the first time one of the first books in which this idea of leaving oil in the soil and leaving coal in the hole, of course, this does not come from any academic writing. These kind of slogans come from the local people, very concretely in Ecuador and in Nigeria, in the Niger Delta, because Shell has been there for a long time. I think there are some people from the Netherlands in the audience, so Shell has some responsibility on this, and then, but Repsol is also there, and Agip is also there, so all companies from many countries are involved, and the local people who have been suffering, one of them, Nimo Base, in fact, in a meeting said, let's leave oil in the soil. So this could become a song. Well, this is the cover of a book that we published a few years ago already with these slogans. And the poster is from a meeting in Africa, obviously. So complementing, as we could say, the top-down policy in action, to tell the truth, isn't it? From Rio de Janeiro to Glasgow, a lot of talk, but not much action, as we see in the killing curve, isn't it? in flattening the killing curve. This has not been achieved, and therefore complementing top-down discussions on taxes, for instance, or quotas, or market, which I'm totally in favor of this kind of public policies. We can also consider these grassroots actions of local people complaining against coal mining or oil exploitation, or also coal-fired power plants, as we shall see. Now I start with Korea, because in Korea, after 2008, there was a discussion very strong in Korea about a new Green Deal. A new Green Deal because of the previous crisis in 2008, in which investment would go mostly for greening the energy system with solar energy and with wind energy. And this, now we know the results, and the results is that this did not happen. This did not happen because it was too little in a way, and too late, and too expensive probably. And what we know from Korea is that of course there are complaints, and there is complaint like in this case that you can read quickly here, which is a very big coal-fired power plant, or a park of power plants of 6,000 megawatts of power, south of Seoul, where some people are complaining about, but without success in Korea, because this is going on. And also I put this because one can make a first estimate of the amount of coal which is being burned there, and the corresponding amount of CO2, I don't know which here, or will come later, of CO2 which is being produced. I'm going to talk about CO2, not the carbon, the 11 gigatons of carbon that Susan mentioned before. In my talk will become 35 more or less gigatons of CO2, which is what is in question, isn't it? This should be reduced by half quickly, as there is an agreement on this. And how this will be done, I don't think it will be done, but I am discussing from an optimistic point of view, which could be done relying on movements such as this. These are people demonstrating in this case in Korea against these enormous coal-fired power plants. So I'd say this again, there are top-down policies, but also bottom-up, so to speak, social movements concerned with this. Not all movements, not all people around the world complaining against oil exploitation, for instance, in the Niger Delta, in Nigeria, Ogoni people, or Ijos, or in Ecuador, against Chevron, Texaco, and in so many other places around the world, are concerned about climate change. But in Europe, we know, for instance, that the Ende Gelände movement in Germany, complaining against lignite coal mining near Köln, no? And in Lusatia, which is near Berlin, in these two places with some success, because coal is going to be phased out in Germany. So these people are mainly concerned about climate change. These activists are mainly concerned against climate change. But quite often, these struggles from the field are motivated by local issues. But more and more are also motivated by the global issue of climate change. I'll mention here very recent grassroots movement with some success. One very recently, a Goldman Prize, which is a prize for environmental activists, was given to Kimiko Hirata of Japan, who is like a leader of the so-called Kiko network, which they have managed to stop a few coal-fired power plants. Because in Japan, after Fukushima, there was a kind of coal renaissance, which has not been very successful either. As if Japan would need even more energy, more electrical energy. And it's a bit, going back to coal, imported coal, because people wanted to stop many of the nuclear power plants. So he got a prize for this. And in Canada and the US, in a very optimistic estimate, they say that all the blockade movements against the Keystone pipeline and then the Dakota pipeline and so on, that Biden has more or less ratified this, stopping these pipelines, represents the amount of carbon which I mentioned here, which has been avoided. I think this is too optimistic because what it says is not forever. And there might be what we call in ecological economics, or normal economics also, we call leakage. Leakage means that you leave the oil or the coal in the soil here, but it's produced somewhere else. But somewhere else has to be somewhere else in the planet, cannot be in the moon, isn't it? Therefore, there are limits to leakage if you look at the, say, small countries like Ecuador. No? If Ecuador would have left in the soil the oil in the Yasuni ITT field, which I was very much involved in this from 2007 to 2013, and was boycotted by the president of Ecuador at the moment, this idea of leaving oil in the soil. Well, in Ecuador there is not enough oil everywhere to say it will be substituted by some, but could be substituted by oil somewhere else. All this has to be discussed in the context that there is not oil everywhere, or gas everywhere, or coal everywhere, and that perhaps we are reaching peak oil, not certainly peak coal or peak gas. So one can look at this from the supply side or from the demand side. Quite often the top-down policy is seen from the demand side, how to reduce the demand through taxes and so on. I am talking from the supply side, to use this kind of terminology. So for achieving a plausible round figure of 20 gigatons, billion tons of CO2 reduction, no? More or less, this is a plausible number. It's about half, or a bit more than half, what is being produced now, and we're increasing again the emissions this year because of China and India after the pandemic. So we have not reached the peak of emissions. We have not reached by far the peak in the killing curve, but not even the peak of emissions we have reached. So this is needed to be done quite soon. And there are several ways of looking at this, and my own way here is just this bottom-up way. This is a photograph from India in February of this year, where the girl in the middle is Disha Ravi, who was put in jail for demonstrating like this, because she has become a kind of internet friend with Greta Thunberg, and she belongs to Fridays for Future in India. And the cardboard she's showing says, fund farmers, give money to farmers. In India, don't give money to the coal industry. Because as you know, India is going towards a coal transition, not away from it. He's going to increase coal because, well, I mean, that's what we Europeans did 200 years ago, or even until 1914, isn't it? And even a bit longer than this. So India is doing this, and she's complaining. No, it's not she. I mean, many people are complaining. And she's a very short, well, I think it's quite remarkable, this kind of young people being aware of this, but not just in Stockholm, also in Bangalore in this case. And now I'll go faster. This is an example which is in the Atlas from the South Cotabato in the Philippines. And this, you can read the banners, and the banners are in Tagalog, but also they are in English, so not to call money. So we know that this, if I remember well, the amount of coal that would be there would be like 25 or 30 million tons of coal, which is not a lot, but everything helps. And the local people, in this case, did not mention, as far as I know, still climate change, because this is from 3 or 4 years ago, but they mention only the local effects. This was in the Philippines, and this is the photo of a grandmother, activist grandmother, killed a few years ago. In the Philippines, they kill many activists of different kinds, but also environmental activists. And you see what is relevant here. Well, Katarungan means justice in Tagalog. So it's about climate justice, but explicitly, and she's complaining, however, about a local coal stockpile and also a coal-fire power plant in Mariveles near Manila in the Philippines. And now they have declared, the people who sympathize with this cause in the Philippines, that the 1st of July, the day she was killed, is the day of climate justice, or climate justice martyrs. The elders makes these things more visible, but they are already exist. No? One wonders why this is not more often in the newspapers everywhere in the world. I shall show another case, or another grandmother activist in South Africa in a minute. But before, some cases from Japan. One of these two cases, but there are like 15 cases in Japan of coal-fired power plants stopped in the last few years. One was stopped with success near Tokyo, and the other was not. In Soga, they built it in the last 5 or 6 years, and it's working. And it's working, and the one is working in Chiba Prefecture is, again, not as big as the one in Korea, much smaller, only 1,000 megawatts. And through this, there is like a consensus, more or less, which engineers would probably agree here in the room also, that 1,000 megawatts of coal, of course, depends on the coal, isn't it? And or the efficiency of the coal-fired power plant, but represents about 6 million tons of carbon dioxide per year. And there are thousands of these coal-fired power plants around the world, and more being built just this moment in China, around China, in the Belt and Road investments, and in other places. So coal is not going out in the world, coal is increasing. People call the production. It's not production, it's the extraction of coal, because coal was produced millions of years ago. Is somebody mentioned before, is different a stock of photosynthesis, bottle photosynthesis, than, well, bottle photosynthesis would be a bottle of wine, isn't it? But it will be a bottle for 6 years or 10 years or 20 years. But of course, this is millions of years of being bottled, and now we use it very quickly. It's different from current photosynthesis. So this is what you all know here. So this is interesting because, as you see in the explanation, is a small proportion of the emissions from Japan, but if you add a few of these, would make a difference to Japan emissions, which have been growing, although the economy has not been growing. This is from India, and it's a different context socially. There is grandfathers, probably, perhaps grandchildren, who are celebrating that some years ago in Karnataka, in a place called Chammalapura, they managed to stop, because of local reasons, because they are local farmers, a coal mine and coal-fired power plant also of 1,000 megawatts. Of course, there are many being built right now in India. And in India also, this is from a few weeks ago, in Chhattisgarh, about 300 or 500 Adivasi people believe they live in fear. As you see, they walk on the side of the road, not in the middle of the road, to leave space for the police and the lorries, I suppose, marching 300 kilometers to the capital of the state to complain against big coal mines, new coal mines, by either the national coal company, the state company, or by Adani in Chhattisgarh, Jharkhand, Chhattisgarh. This is the center of India. In terms of international trade, one could call about internal colonialism, different from exports from say, Latin America, of iron ore from Brazil to China of the North. And, well, it's a very, indigenous people have been there for thousands of years. And so they don't, any of the banners will talk climate change yet. But the spokesman for this, or the spokeswoman who leading the march, they already know about this. They have learned recently, 2-3 years ago, and they say, of course, coal is bad for us because we are being deprived, displaced, isn't it? And this affects thousands of hectares and thousands of people. Now somebody is from South Africa, which is also a big producer of coal, or extractor of coal for export. And also, I'll show this photograph of this woman activist, Fikile Natsangase, who was killed just about 1 year ago, 1 year and a month. And she was complaining against a mine, a coal mine, that was invading her own village and territory. And they formed a local movement called Movement for Environmental Justice. And this killing of activists takes place in the world in 2 ways. One, when there are demonstrations and the police shoots the demonstration, or when the companies perhaps, or the government, or some people pay somebody to kill just one person, or 1 or 2 persons. She was killed, the grandchildren were there. Since I am myself a grandfather, I am impressed by this grandmother activist being. And we have a collective article on women activists killed, published 1 year ago in a journal called Journal of Political Ecology, with a very incomplete census, because there will be hundreds of such cases in the world, not only with coal, but oil and gas, also with metal mining or eucalyptus plantations and so on. What I put this here because if you look at the lower part, and you can see it even from the last row, there is a small sign saying, "Keep the coal in the hole." So they have learned this kind of slogans also in the last 10 years. In Jamaica, there is also a question which I have in this article, or about another 1,000 megawatts plant. And this is because of bauxite mining, and then you need a lot of electricity, as you know, to have aluminum. Aluminum is being used for windmills and for many other things. Also, just by the way, 2 days ago, when I was already here in Rome, I was talking in Ecuador in a session on balsa wood. Balsa is a very light wood, called boya also in South America. And this is being exported now to China. In fact, it's being grabbed by Chinese companies for export to China for windmills because it's very light and is used for. So the electrical transition has a cost, not only in terms of lithium, and so we are, I think, all in favor of sodium batteries, but also has and there are also lead batteries, which are even worse from the point of view of pollution, isn't it? We have many cases in China of lead batteries conflicts in the Atlas, but also in terms of this wood for the windmills. I'm sure that technology can arrange many of these things, but this is the situation now in Ecuador, with balsa trees being in the coast and Amazonia being destroyed very, very rapidly in the last 1 year or 2 years. This is, I go back to aluminum, electricity of aluminum. Aluminum needs a lot of electricity. And in this case, what has happened is that this coal-fired power plant is not being built. The local people in Jamaica managed to stop it using climate change arguments, but it's going to be built not as with coal, it's going to be built with liquid natural gas, which is a big fossil fuels increasing very fast, which I'll mention later because I'll mention the Total French company, which is very much active in building factories of liquefied natural gas. So now I'll see very briefly some oil and gas conflicts. What I'm doing is in a very different style, which was the previous presentations. It's very anecdotal, if you like, but I want to, well, I mean, to keep you awake and also to get you interested in the topic. At the end, there are some more sort of generalizations and conclusions, but I am more than halfway through it. So these cases I show in Argentina and Mexico were against fracking of gas, isn't it? And they are interesting because one sees already indigenous people even in Argentina, Mapuche people complaining in Patagonia and Neuquén against gas fracking, because in the world there is a kind of indigenous revival, indigenous people in the last 40 or 50 years, perhaps because they are slowly disappearing or becoming integrated into national society, but they have revived socially and politically with their own identities and names, isn't it? And this is very much linked, I think, to resistance to extraction of many kinds, because they live in the frontiers of extraction. They live in the commodity extraction frontiers, including the Arctic, for instance, which is a frontier of extraction of oil, gas, and nickel, and other metals. So this is very far from Argentina and from Mexico. I don't know whether there's anyone from Norway. Norway is a big exporter of oil, as you know. But also in this case of the Lofoten Islands, they made an exception after a big debate for many years to leave the oil under the sea. And I have some calculation here of the amount of oil that this implies. I don't know whether, we can discuss the Lofoten Islands afterwards. Here we have different values, no? The cod fish, the beauty of the place, the tourists that go there, the oil, the money. Norway has too much oil and too much money, perhaps, already, so they don't need it very urgently. And the Labour Party changed sides, and now they have become more ecological and less based on the unions, perhaps. This is one of the reasons. But it's one reason to be optimistic, isn't it? That these things happen. Leaving oil in the soil is not just a utopian idea. This is happening in some places, as also with the South Dakota pipeline, or not, the Dakota Access Pipeline, which is linked, all this in the States and Canada is linked to the Alberta heavy oil and so on. This is in southern Italy, since we are in Italy. And this is a failed kind of struggle because this pipeline is being built coming from Anatolia and from Central Asia, gas for Europe, because in Europe we import gas from everywhere, from Putin land and from Central Asia and from Algeria, from Nigeria also, and we import gas from everywhere. And we don't import anymore the pepper as Vasco da Gama did from India, or silver or a little bit of gold from Minas Gerais, as in the time of Columbus and Pizarro. These were little preciosities, quite valuable in money terms, but not very heavy. Now, no. Now with pipelines and tankers and so on, the amount of materials, tons of materials that travel around the world have never been so large as today, isn't it? And Europe is a net importer of energy, especially since we stopped mining coal, isn't it? But even with mining coal, because the amount of energy we use is much larger than at any other time in history, and all this is not only energy or fossil fuels, it's other materials also, like soybeans from Argentina or soybeans from the Cerrado or the Amazon border in Brazil. So I like this, for those who are Italian, this slogan, né qui né altrove, which means exactly when in the US, the environmental justice movement invented an acronym called NIABI, not in anyone's backyard, because they were being often blamed as NIMBYs, isn't it? NIMBY means not in my backyard, and this is a kind of anti-environmental slogan or terminology. And they say, no, we are not NIMBYs, we are NIABIs, not in anyone's backyard. And this in Puglia, they translate it into Italian. And there have been some movements in Italy called no movements, but which are quite transversal, I think, and they are not NIMBYs, although this is a question that could be discussed. If they are into stopping gas, it's very easy for them to link this up with climate change issues, isn't it? And with climate change issue is not a NIMBY issue, isn't it? It's rather a planetary issue. The last two examples I want to show, they are really important geopolitically and in terms of human rights. And one has to do with Total. Total is also active in the Arctic, in California, in Mexican California, and so on. With this kind of new, it's not quite new, but very promising technology of liquefied natural gas, which implies a lot of energy to liquefy the gas to minus 160 degrees, I think, and then, but of course there is a net gain in energy because the energy has been produced, is in the gas deposits, and this is between Madagascar and Mozambique, in northern Mozambique, and there is sort of war going on, or about to start, to get this gas out. And as I said here, is about, in oil equivalent, is about 60 million tons of oil per year, which must be more or less the use of oil in France in 1 year. 60 million tons, 1 ton per person, perhaps. So the next one is also in Africa, in Western South Africa, between Namibia and Botswana, and this is the last one I am showing. And this is something which is still very premature. We don't know how many. There is a small company from Canada announcing a big discovery of oil, perhaps to make money selling the shares, but perhaps there is a lot of oil. And this oil is located in this internal delta in Botswana, which is a river coming from, which does not go to the sea, and this an area, the one there, which is very rich in biodiversity, in the meaning elephants and rhinos and so on, also a small-scale biodiversity. And this is something which is now, right now, in this month, under discussion. And you can imagine I don't know what the Canadian embassy is saying in these cases, but let's assume, which is very likely, that Recon Africa, a small company, sells this to Chevron or sells this to Total or some other big company, which is the power of a state, the United States or France or Italy, compared to the power of the state in Namibia or Botswana, isn't it? Or compared to the power of the San people in the Namibia desert, no? Very little. So it's easy to bribe people or to give a good contract with money terms or to buy the right in money terms to do this. And the damage to the environment and to the people and to future generations because of the carbon dioxide, this is not counted in the belong, no? in the balance sheet of any of these companies. So the economic accounting of company excludes the environmental liabilities. This is a principle of accountancy. Accountancy, I think accountancy was invented in Italy in the 13th century or 14th century. Of course, one could say they forgot about the environmental liabilities in Toscana. They were not very large, perhaps, but now this absence of proper accounting, which should not be in money terms, should be in different values, sacredness in some cases, livelihood, no? Ecology, these other kind of values, the value of the future for. So the conclusion is that the industrial economy, I said this yesterday, is not circular at all. It is entropic, and it is more entropic every day that passes because we're using more exhaustible resources which are not being produced, are being extracted, and we are dissipating And even, of course, I know that in energy is very clear the second law of thermodynamics. And I know that there is not equivalent law for materials. I know, I've read Clausius from the 1850s, and at one point he talks about something like dissipation of materials, but it's more like a question of experience that you cannot recycle everything, the materials, for instance. And Georgescu Reagan, who wrote this book, The Entropy Law and the Economic Process, just 50 years ago he published it, he thought that, as he had a sort of mantra, they're saying matter matters too. It's not only energy that matters, matter matters too, because he liked to put an example that if we go with a lorry from motorway, all the rubber is being dispersed, isn't it? We could go in the motorways and keep all the, what would be these, the particles, the molecules perhaps of the rubber, and put them back and but the cost in energy and time and so on, and there is no technology to do this. So all this gets dispersed, lost. It's not lost in outer space. I mean, it remains in the earth, no? But it's true that both energy and as was shown before, the energy from the sun, the current energy from the sun, you said is 10,000 times the amount of energy that we are using, so there is no problem with the energy. If we had the technology to use this better than photosynthesis, which only converts about 1% of solar energy, isn't it? But one question would be the matter. This links with the previous question about lithium, because there are problems with lithium, including in Spain, in Cáceres. The local people are against a mine because they say, I mean, why should, anyway, it doesn't matter the local reasons, but there are also many other similar conflicts with other materials, isn't it? So the energy transition, which in fact it means the electrical transition, has a cost in terms of new materials, but also space. A windmill park occupies a lot of space, and people in the Isthmus in Tehuantepec in Mexico or in Gujarat in India, pastoralists, complain because they say, it's not the windmill, it's just the roads and the towers and so on. So this cost, social cost and environmental cost and space cost and so on, of the electrical transition must be taken into account in a manner of accounting which is not crematistic accounting. I say crematistic because we are in a very classical building, and in fact there is some Greek inscriptions very near here which I saw before, and crematistic is an old word that Aristotle used, meaning money-related kind of economy. And he compared this with oikonomia, which was the real economy, we would say, or the real economy of provisioning the oikos and the polis. So we're still there. We are still in this kind of discussion, which also was repeated by other people later. So the last one, well, this I already said probably. So there is no transition yet. All these new sources are added. If one looks at China or India, China, for instance, is at 4 billion tons of coal per year of extraction, which is 3 tons per capita, isn't it? 3,000 million. And this is like England in 1914. So the world has already been, the Western world, we have already been there. But why China should not be there? They would say, well, they should not be there because this cannot go on like this, isn't it? But how the energy transition will be in China is not so easy to see how they are going to do it. So now to come to the last point, which I announced at the beginning, one could make like a very rough estimate of all the attempts which are around the world. This estimate has not been done. This is like a first attempt. This has been published already, so I cannot now repent suddenly very much about this. If there are some mistakes, they are already published. But it's a kind of rough estimate and what they show is that about one-fourth of the reduction that should be done of these 20 gigatons of CO2, because if we are nearly 35 or 40 and we have to reduce by half quite soon, and the rest will be absorbed by the oceans with getting more acid every day than passes, isn't it? That you didn't mention because you have no time for everything. And for the new vegetation, which in Amazonia now is producing perhaps more carbon dioxide than they are absorbing, isn't it? At least in many regions. Therefore, the net carbon is a very sort of mysterious kind of concept. But let's assume this is true, that we can still put like about 20 gigatons per year and come back from 40 to 20, isn't it? Taking into account population growth and taking into account economic growth, that everybody seems to like still more economic growth. So it's not 40, it will be 45 or 50 gigatons per year produced in the next few years. Therefore, of these 40 that should be reduced to 20, of these 20, perhaps 5 or 8 or 4, something like this, can be attributed, increasingly attributed to these local movements to keep the LFF movements, leave fossil fuels on the ground. And this is what I calculated here with other people, of course, and we came to this, and this for reference. This is the article published recently where all this is explained. Since it is very recent, there are no yet any complaints about this, but they might come. Thank you.
Thanks a lot, Joan, for this fascinating and very concrete talk. There will be some questions, I think, and please, yeah. George.
Thank you very much for a fascinating talk. Amongst environmental people who are concerned about fossil fuels, there are two types of discourse, and I wonder if you could comment on them. One that says we should stop immediately any fossil fuel extractions, and in particular we should disinvest from companies involved in it. And another discourse which stresses the importance of moving out of fossil fuels, but to do so in a way that allows energy security going into the future and concentrates on moving out of coal immediately, but keeping gas as part of the mix until renewables and nuclear, possibly nuclear, can substitute for it. Do you see a tension between those two different narratives about how to achieve net zero?
Yeah, well, I see quite a few tensions in, this one would be this idea of stopping immediately extraction of fossil fuels just will not happen, it's impractical. There's now some people saying that the states in the world should sign a non-proliferation treaty regarding fossil fuels, similar to the non-proliferation nuclear treaties, and this will not happen, and because China and India will not sign this, and other countries. And regarding coal, and all exporting countries will not sign this for all. What might happen is a decline in the emissions of carbon dioxide coming from a decrease in the burning of fossil fuels, and a change also in the land use, which is moving in the opposite direction, I think, although I'm not sure because there are more forests now in Italy and in a few other places. Leaving land use changes aside, with fossil fuels, what one could hope is through a mixture of measures and and meetings, and including COP27, 28, 35, 45, in some years, that some taxes on carbon dioxide might be imposed, for instance, and so on. But also through these grassroots movements, isn't it? But the second part of second alternative of including nuclear, I think I don't think, although this is very much discussed now in France already, this is such a, well, science doesn't know exactly what to say. I know from the Lincei booklet that Alberto has produced very recently in English, that Lincei believes that we should speak science to truth, speak truth to the powerful, isn't it? But in this case of nuclear power, I think there are so many uncertainties. We don't know when the next accident will take place. But the longer the nuclear power plants, which are already 30, 40 years old, are kept active, the more likely, I think, talking rationally, is that an accident will take place. If an accident takes place, say, well, I'm not going to mention the countries, but where this might take place, but this will change suddenly, overnight, the whole discussion about nuclear. So there are many uncertainties that this idea of a smooth transition to a new energy system, to me, seems this will not happen. It will be a very messy kind of long-drawn discussion in which the perception of climate change will be increasing, reaching places like South Africa, which exports a lot of coal, Colombia, that exports a lot of coal, India, the center of India, where climate change, of course, is not in the Vedas or in the religion or even in the science that is being taught still at the primary schools. So this will be for the next 20 or 30 years, that these things. There might be technical breakthroughs on the side of solar energy and batteries. Yes, this might happen.
Actually, the last part of your answer partly answers my question, but I will still pose it. So I would like for you to compare apples and pears. Actually, real apples with hypothetical pears. And the real apples are the damage caused by generating energy from coal, as you very clearly and convincingly demonstrated, the damage on our climate, on generations to come, as well as the damage on the health of the local populations around the coal-fired plants. So these are the apples, the real apples. How will you compare it to the statistical low risk that they're associated with the generation of nuclear energy? Given the fact that France, for instance, has generated 70% of their electricity from nuclear plants for quite a while, and there are a number of other data that shows the usefulness of this technology. So that is, of course, a hard question. That's also why I put it. But I will put it in more concrete terms, having this question in mind. If you were the president of the world, would you tell South Korea to build the necessary number of nuclear plants with the newest safe technology within the field in order for them to close their totally contaminating coal-fired plants within, let's say, 10 years? Would you tell the Indians, please don't buy or build this 1,000 new coal-fired plants that you need to catch up with China and the rest of us when it comes to general wealth for your population, and instead use the newest nuclear plant technology to replace these new coal plants? And if they are built, they will neutralize the gains the rest of the world have made by introducing sustainable energy, wind energy, and solar energy. These savings are simply nullified by the new coal plants which are being built in India and other places. Isn't it better to replace those by nuclear plants?
Yes. Well, I didn't talk about nuclear plants, but I think these are very relevant questions. The first part of what you said about the damage from coal, the local damage from coal. For instance, I have a postdoc from China who is now back in China, and she has a recent article on pneumoconiosis, which which is called black lung in English, in colloquial English, because the miners got black lung, or people living near coal, which is similar to silicosis, I understand. And this article by Juan Liu, that's her name, is about like a kind of plague of pneumoconiosis in China. And I think that in India must be similar or even worse, but not similar because India produces much less coal, 1/4 that of China, but the precautions probably are even less than in China. So I totally admit you're part of the question about nuclear coal mining, isn't it? Apart from the carbon dioxide and pollution in the cities like Delhi. Delhi these days they have, I think, shut down large part of the activity in Delhi because in winter what happens in North India is that both they are burning the stub of the crops and at the same time the coal-fired power plants are producing as they do. So more or less like this used to happen in Europe, like in London in 1952, isn't it? And London got rid of the coal or the coal pollution through other sources of electricity, which must be gas and nuclear probably, or some oil at the beginning. Anyway, so the alternative to nuclear I am against, but not as an honorary, temporary member of the Rinche Academy, to put it in these ways, coming from Galileo and taking science very seriously because I don't have a scientific expertise on this, but I know India, for instance. In India, they said they were going to build many nuclear power plants. They are not doing this because of local opposition in some places, as Jatipur, and in other places because they don't know how to do it safely, to tell the truth. In the south of India, in Kalpakam, they are building a breeder reactor with Russian technology and some French help, because the French help has a kind of, the French state has a kind of love affair with nuclear that I think from the Joliot-Curie family. Or the Communist Party in France was pro-nuclear, which is also the case in India, and not in Germany, for instance. So this goes much beyond any kind of normal science, isn't it? You can explain why Germany is not using or is going to shut down the nuclear power because the Germans are, more risk adverse or more scientific. I don't think they're more scientific than the French, but you have this very different. So going back to Kalpakam, this is the kind of breeder reactor which was stopped in Krimalville and has been stopped in Monju in Japan. So breeder reactors are not very successful. For a long time, the nuclear industry said, we are going to beat the entropy law, so to speak. We're going to become a circular economy. The plutonium is going to be used again. So since this is not being done, except perhaps for military purposes in some places, what happens with the nuclear industry is that there is a waste which will last for tens of thousands of years. Plutonium is 20,000 years, the half-life. So if you have a solution for this, we could have a meeting some other day because today will be too long to discuss this, but there is no solution. So I think, as you said, apples and pears cannot be compared. The 3% GDP growth, or 2% in money terms cannot be compared with what will happen to humans and non-humans in 80,000 years if a plutonium deposit in Nevada starts to leak, isn't it? So this is what my view of nuclear. And you said that we have some probability, I don't know whether you said this. In fact, my own view is that we have no idea of the probability of a next nuclear power accident. Will never happen. Nuclear accident, I mean 3 Mile Island, Chernobyl, Fukushima, this series. How is it going to be continued? Perhaps will never happen. I don't think it will happen in my lifetime, perhaps, but might happen in the next 20 years. So we don't know. So risk analysis and probability analysis is useful for many things, but not to predict nuclear accidents, I think. So this is what a French philosopher or writer called Jean-Pierre Dupuy, who teaches in Stanford and in Paris, calls le catastrophisme éclairé. This would be our principle, to think, to learn from these catastrophes. That's what my own view. But you went outside the topic, which was fossil fuels, and you touched nuclear, and yeah, I am an old anti-nuclear militant from my age, and but we have many reasons, I think.
Excuse me. We have 3 more questions, Bengt, Sheard, Thomas, and then I have to close to have time enough for the final session, the discussion amongst the prize winners, and it would be interesting to have this, and some concluding remarks of Quadro Curzio. Bengt, Sheard, Thomas.
Thank you very, very much for your presentation. I wonder, also including the quite challenging and, in a way, encouraging review of all the activities going around in the world here. I wonder how you regard our activities as scientists and scholars and academies. What further actions would you like us to take now?
I mean, I think you should do what you do now. I mean, what else can you do? I mean, a scientist, even myself, who touch so many issues, because, but there are things of which I am totally, I could learn it, I suppose, but I have not an informed opinion about the livelihoods of batteries becoming commercially viable in the way that Jean-Marie Tarascon explained, isn't it? And so we should keep to our own expertise as scientists. But this is not an excuse not to try to understand what other people say. For instance, I myself was an agricultural economist many years ago. So peasants know a lot about agriculture, although in fact they invented agriculture. Women peasants probably 8,000 years ago, but they don't know about nitrogen, phosphorus, and potassium with these words. Perhaps they use other words to explain than lentils or feijão, and leguminous crops are very good for children, because of the protein, but they don't know the word protein. So there is a lot of knowledge around the world. But this would not apply, for instance, to climate change. It does not apply to nuclear physics. People don't know about this. So how scientists can work with the normal citizens and not to think that we know everything, because it's not true. It's impossible for any person to know it. Well, for instance, in a meeting like this, I like to joke a little bit that if I, yesterday or 2 days before yesterday, talking to Ecuador about balsa trees, I didn't know about balsa trees. Many of us go through life expanding our ignorance, isn't it? Expanding also our knowledge, but more our ignorance. And this is, well, it's a very good way of living, expanding all the day a little bit your ignorance. And giving advice very carefully and always based on what is relevant for social groups or for people concerned, for people who are suffering. Look at the many cases of technologies. Well, there is these reports from the European Environment Agency. At the time I was there, but they did not take part very strongly in the reports, which are called lessons from early warnings. And there are like 20 or 30 examples, including asbestos, low-level radiation, DBCP for banana plantations, which have left many people sterile. So who gave the first notice that asbestos was killing people through asbestosis? It was, according to these reports, a factory inspector in Britain, and then local workers living there. Was not any chemist or any medical people. So this happens quite often, I think. So as scientists, we should respect sort of indigenous knowledge also, but not in everything, isn't it?
Sheard?
Yeah, thanks very much for this very interesting presentation, and also bringing some nuance into this issue about absolutely safe technology in the nuclear domain. Because you have already mentioned the waste disposal issue, fundamentally not solved. Of course, also, when we talk about nuclear energy, we cannot avoid talking also about uranium mining,
Yes.
which is also not so environmentally friendly. Needless to say that also quite a few nuclear reactors have been built on tectonic fault lines. So we have to live with a lot of uncertainty here and to find a balance in dealing with them. But whatever we do in the subsurface, of course, has consequences. And I think your review basically revealed very much, let's say, the issue that this is not a trivial issue. And in that context, I think it's wonderful that we have here now a discussion about some possible solutions, and also to learn from you that the issue is more urgent than ever. So thanks again.
Well, uranium mining, for instance, in Namibia, there is uranium mining by the Rio Tinto company, and so Namibia is a very empty country, but I mean, it's a question of colonial relations also, which we should talk about it because they exist.
For us, the members of the committee who had the pleasure to read your work, it was very interesting to see how it turned into activism, and very convincing the way you put it. Could you go somehow the other way around and say, what do you or what do your pupils, the younger scholars in your field, what do they learn from activism? And I mean, you mentioned in the end, you mentioned an article, and but you were very quick on that. So what is the impact of the environmental and political engagement of you and of course of all these bottom-up movements for your own research and for the research in the field?
Now, one way of learning about what happens in reality, well, is to be an academic expert on something and do a doctoral thesis and become perhaps a mixture of chemists and anthropologists who would really go into what the oil industry is doing and geologists also in Ecuador or in the Niger Delta, to give these examples. But another way of learning, clearly, because I know them and I've seen how they learn, is for activists to try to help the local people who are asking for help when confronting the companies or the government and so on. And this happens everywhere, because of this issue of uncertainty, isn't it? For instance, in China, some of the conflicts that we collected in the Atlas, which is not yet, China is not well represented because there are many more than we have collected. But one issue that some years ago was very alive was incineration of waste in cities, as we do in other places, or in cement factories, which is done. So, and people in China, as in other places, learn the word dioxin and furans. Well, the chemistry of dioxins and furans is really complicated for any normal person, so to speak, who is not a chemist who knows this, because there are many different kinds and so on. But the word itself, depending who says the word, you cannot be totally ignorant. You have to say something plausible to people, either to say this is not dangerous because the incinerator will work at a very high temperature and so on, or to say, well, an accident is always possible and dioxins. For them to complain against this because their fear is just, at the beginning, just a fear which is not justified by any facts, isn't it? But the facts remain uncertain. quite often in reality, isn't it? And well, this is what some people call the post-normal science of rabbits and Funtovit's facts uncertain, values are in dispute, the stakes are high, and you cannot wait. A city administrator in China, I suppose, would say, I cannot wait 20 years until we convince everybody. We'll go ahead. In China, I would say, because the political party has said, build incinerators, and if I don't do it, it'll be removed, isn't it? But it's more or less the same thing everywhere. We have to take decisions in the presence of this kind of thing. So this is what one learns when trying to learn from activists also. Activist is a very wide word. I mean, it could be all kinds of people who become, like some of these women I show from, the one from South Africa is not an expert on anthracite mining, but she has the mine 20 meters from her home. It's a good way, it's a good lesson. You learn lots of things in this kind of situation. So thank you for.
Thank you. To end this session, this panel, I give the floor to Quadra Curzio for some closing remarks.
Thanks, Vice President Professor Kuhn and Chairman of this session. I have followed with admiration the speech of all the three prize winners this morning, because in my opinion there is a very, very remarkable convergence on the same issue, of course, and to find out solutions. Before making some consideration, especially on Martinez-Sarrier's report, I am an economist, political economist. I stress again my appreciation for the Balzan General Prize Committee for having found out these 4 prizes, which are in a certain way converging. So it has been a very, very important innovation. So thank you for what you have done. Before choosing the title of the prize and then choosing the winner of the prize. Very, very good indeed. Going on a little bit on the speech of Martinez-Sarrier, but I think by side, touching also the previous speeches, I make 3 considerations. The first one, which seems very obvious, is that history matters. History matters. No one of us can forget history. It seems to be a very general speech, very general, too general. In my opinion and in my competence, it is certainly very wide, and I have no competence to go into what I call the fundamental history. There are very types of history. The fundamental history is very, very difficult indeed. Someone say, well, history is not so complicated. You read someone, you remember, and you know history. You don't know history at all. So fundamental history is crucial. I would like to go back to some classical writing of fundamental history, but it's not the moment to do that. Fundamental history matters. Secondly, the collaboration among different sides of human researches is absolutely fundamental. What we call interdisciplinary is not a kind of mixture to know something of everything, but is absolutely essential more and more. Third point, sometimes the scientists in human sciences, social sciences, humanities, generally speaking, don't have enough competence to understand the physical, mathematical, and all these sciences. So the communication is a fundamental point too. We must learn how to communicate. Otherwise, we cannot collaborate. Communication is fundamental. Now I go into some of the aspects of Martinez-Sayer's speech. I knew him since many times, not personally, but his work has been a landmark in the history of political economy. History doesn't mean that he ended. Political economy received by Martinez-Sayer a crucial contribution. He says ecological economics. I would like today to say ecological political economy. I don't like economics, I like political economy. And I explain why I like political economy, and I'm sure that Martinez-Sayer agrees fully with me. I go back to two lady prize winner of Balzan Prize. One is Bina Agarwal. Bina Agarwal has been a path-breaking like Martinez-Sayer in her field. Just to give a kind of concrete consideration, she explained it with the scientific analysis, statistical analysis, anthropological analysis, and all these things, that when the women have the property of land, the environment of that land ameliorate, improve. Of course, the education of child and all these human aspects. So Bina Agarwal has been really a path breaker like you. Some consideration about the history of economic thought. History of economic thought is very important indeed. I am glad that Martinez-Sayer quoted in his speech Giorgio Nebbia, who was one of the pioneers in this field. But I would like to stress another personality who was, in my opinion, a very, very foresighting personality, Aurelio Peccei. Have you heard about it? Aurelio Peccei founded the Club of Rome in 1986 or something like that. I think 1968. The Club of Rome was, as far as I know, the first club which stressed the risk of the climate change, underdeveloped, under convergence, north-south, and all these aspects. The Club of Rome, and I'm quite proud of that, has been founded here in Accademia dei Lincei in 1968. And it had a remarkable success in a certain light of the history of political economy. The so-called Meadows report were two reports elaborated by the MIT and published in 1972. And the Meadows report remained, in my opinion, a crucial step in what we call ecological political economy, absolutely fundamental. Moreover, what seems to me important to stress are two aspects of this person, Italian scientist, or more than Italian scientist, Italian genius, in my opinion. He worked in a factory of cars, Fiat. He left Fiat to go into these topics. He went to America Latina and he went in many parts of the world. And then he organized the Club of Rome. Report of Meadows report in 1972. But what is less known, and it is important for me, for the history of sciences, he was one of the founders of the International Institute of Applied System Analysis, which was founded in Vienna and was a kind of modeling of the prospect of the growth, or more, the development of the world economy, population growth, and all these aspects. In my opinion, these are steps not only of political economy, but step in the forecast and the danger we were since there under doubt. So the history matters always, and to go back is absolutely fundamental. Aurelio Peccei, in my opinion, has been a truly genius, like other two persons I want to mention. Both got the Prix Nobel, not the Prix Balzan, because the Prix Balzan was not yet started. One is Gunnar Myrdal, who was a political economist from Sweden, very, very clever and another genius. Under development studies, the problem created by the race antagonism, kind like that. I don't word exactly what I mean, but it was really a fundamental step in political economy and more than that in social sciences. Gunnar Myrdal, Prix Nobel 1974. And his wife Alva Myrdal, who got the Prix Nobel in 1984. Alva Myrdal, born Reimer, got the Nobel Prize for Peace for what she does or has done to promote disarmament and to utilize the resources of disarmament for development, not for armament. So these are persons which, in my opinion, remains or should remain, certainly in my mind, in the history of social sciences because they gave an enormous contribution to social sciences. Now I do two comments which are much close to what is happening now. The first one is the Green Deal that Europe started within the Next Generation EU. Remember that the Green Deal compulsory puts 40% of the financing on the green transition, 40%. This is an institutional step in Europe, very, very important. And every state which receives contribution is obliged to utilize 40% of the contribution, both subsidies and grant, to green transition. In my opinion, we don't realize this institutional step that Europe has started is crucial. Why we don't realize? Probably because we don't understand that there is another step of European Union behind this decision, which is another fundamental step. This Green Deal is financed by the utilization of some financial instruments which are called Eurobond. It's absolutely an absolute innovation. And I had another information. European Union started to issue green bond. So the financial market receive green bond now and can buy green bond. So the saving of financial institution and the saving of any kind of saver can buy green bond. Do you think that someone bought green bond or not one? Well, the demand of green bond was about 15 times the emission of green bond, 15 times. So it's an indicator that people feel the necessity to change. 15 times was one of the most remarkable success in the emission of bond. 15 times the emission of the quantity of bond issued. So something is changing, And we must have, in a certain way, the strength, the conviction is not just and the competence to support these big changes which are in Europe and I hope everywhere. So, and I conclude, remember that the Next Generation EU is a step, a crucial step. The utilization of this funding, 40% to green transition, and the success of this issue of bond are very important indeed. Of course, the world is wide, and no one probably does the same. I mean, I am a little bit an expert also on finance, but in the field of global finance, you find something which is absolutely unbelievable in negative sense, not in positive sense, absolutely unbelievable. I don't mention specific name of firm, but there is one firm, car making, which produce more or less 300, 1,000 cars a year. It's not so bad. Volkswagen produce 14 million cars, Toyota too. Well, this firm of car has a market capitalization, I don't know if everyone knows market capitalization, which is bigger than Volkswagen. And this is absolutely a speculative bubble, which is dangerous because a speculative bubble is not green bond, it's another matter. So world is complicated, but to be aware that some part of the world institutionally are changing is very important. Example might matter. Martinez Ayer talked about the social movement. Social movements are fundamental, but also institutions are crucial, and also economy is crucial. Otherwise, and science, of course, if you have convergence, it's very difficult to reach success. So many thanks to General Prize Committee for having chosen this field of analysis. Of course, my admiration to the winner, and the hope that social scientists, political economy, and so-called hard sciences might collaborate. And we dare not to forget finance. Because if finance go in the right way, you can easily, or a little bit exaggerated, we can reach a success in shorter times. Time is not so wide, but we might get the results much more, less slowly. Too fast, I mean, is exaggerated, and sort of less slowly. So many thanks to all, and congratulations to the General Prize Committee, and of course to the winner. Thanks.
Ladies and gentlemen, please take your seat. I would like to welcome all of you to the last part of this morning session of this interdisciplinary forum. This last part is devoted to a discussion among the laureates, but if there is some time left, certainly also for your input and questions, if not all questions have been answered before. We are the two chairs, my dear friend Marianne Schwegmann, a Dutch historian, and I'm a Swiss physician. We are both members of the prize committee of the Balzan Foundation. So we take some responsibility also for the 2020 laureates of this Balzan Prize. With this, Marianne, up to you.
Thank you, Peter. As you now know, this is the first time that we have a joint prize dedicated to one theme, environmental challenges. And for the further discussions in the committee, I think it will be very interesting to know whether perhaps we can even make another step forwards and create a common research project, because now these are still individual research projects. And also I would like to say how really a source of joy it is that your project, Suzanne, is also fitting very nicely into the common theme. So we could, in theory, make one big research project out of the three expertises. So I would like to ask you to reflect a little bit on this possibility. What would be the benefits if you would be really working together from your own research projects, but within the common theme? And what would be the problems? And we don't expect you to be complete, but just to have some ideas about the concrete possibilities of working together. Because interdisciplinarity now is, I would almost like to say, a holy cow that you cannot avoid. But what it means in practice is not yet always very clear, and it's not so easy to really do interdisciplinary research. So I would like to ask you this rather general question to start with, and I would like Susan to perhaps react first.
Okay, that is not such an easy question. I mean, I think the central thing for all of us is the human need for energy, and how we just choose to use it and how we choose to make it, right, and store it. And from my perspective, I mean, it's easy to make fossil fuels the enemy, but most of us, half of us in this room today are probably alive because of the Haber-Bosch process fixing nitrogen that made possible the agricultural revolution that, you know, made more calories available so that more people could live. So we have to always balance this kind of, what kind of world do we want to live in with what are we willing to pay for that? What cost are we willing to pay? And I see a lot of what's happening now as this, we're bumping against, up against these planetary boundaries. We're, you know, there's no new green revolution that came from genetic modification of plants, at least not yet. We're starting to pay the price of our extractive economy, and so people are pushing back and saying, no, the quality of life is not improving, you know, if we keep extracting coal and polluting our environment. And we all hope that technology can save us, but all technology has a price. So to me, it's really the imagination. What is it that we want human life to be on this planet, and how do we want to interact with that because we have to extract resources. And I feel like we're not challenging ourselves enough thinking that far ahead. So we have the Sustainable Development Goals. I mean, we have attempts to say this, but you know, a lot of what we're doing is reacting to the moment, and we're not planning far ahead. And to what does an economy, what does a sustainable economy look like? What does the agriculture look like in a sustainable world? I don't think we're pushing ourselves far enough. So I would maybe have a less conventional answer, but to bring all three of these things together, you know, I think we have the technology to reduce CO2 emissions. It's whether we're willing to pay the price. We can do it, but it would also involve tremendous social upheaval to do that. And are we willing to pay that price? So I think we need the technologies, the realistic limits to what we can extract, and but also what humans are capable of and what they can tolerate.
Thank you very much. Jean-Marie Tarascon, what would it mean to you if you would be hiring an historian like me for a project? Would it be useful or not? Very useful?
First, I am a dreamer. And indeed, you're perfectly right. We should have really this kind of, you know, attacking this problem in a general way by the early transdisciplinary, by coordinating efforts. And you look, we don't do it. Why? Look at the COP26. Okay, what are the results? Okay, we don't fail. We fail what? Again, we have geopolitical issues and economical issues. I heard people were talking this stuff. What we are going to do different, and as you mentioned, 40 and so on. So these are all the main questions. And again, I think everyone claims there is a big problem. No one wants to face it directly. Because again, if we put people together, I would love, as you mentioned it, to work with you on economics and so on. Because I think the problem is so complex that we need to have all the information. And we don't want to give our own feeling. We want to give really a discussed feeling. You know, because you mentioned things about, I heard about a lot about nuclear. Sorry, but the nuclear energy, we need to know more or less what is the science behind, what has been happening, how this stuff has been progressing. We are talking about, you know, a 4th generation of reactor. We are talking about ITER. These are upcoming technology. We need to be aware of it. And when we say it's risky, everything is risky. When I put 100 kilowatt of energy in a small cap like that is risky. So you need to balance the risk and what we want to do with it. Mm-hmm. And I think this stuff is very important. And now, the questions you are asking me, I am fully agree with you. I need historian. Because as a matter of fact, as a College of France, I just really initiated an initiative where we have sociology, economics, scientific, and so on. And our mission is really to try to discuss between us, exchange, and to have a kind of not general consensus, and then to address the public. In order, this is what is happening and so on. Okay? And I think this is more or less what is very important. And also I heard about Europe. Indeed, Europe is a locomotive in terms of this. 40% the Green Deal is great and so on. And Europe is giving directive, is giving numbers. And great, they want to be climate neutral by 2050. So how we are going to succeed it? I say we will not succeed it, but at least they give the direction. And this I think is great. And I think they try to motivate research and so on. And again, I think I must say this. You mentioned, President, you know, this kind of a car manufacturer that is small. But sorry, but we need to have this car manufacturer because this is the people that I give the vision and which really brought us where we are today. Without this car manufacturer, sorry, but the transportation will not be the same way that it's doing today. So these people are visionary, they revolutionize the world, and we need to work with them. So again, yes, we need to have this kind of multidisciplinary with historian and so on. We need it, and I fight for it, and I have been fighting all my life for it.
Thank you very much, John Martinez, Allier.
Well, I think that, some things I think we totally agree. And so I am going to focus on this. I think this idea that we three all are interested in energy and society is obvious, is what we have been discussing. In fact, we got the prizes because of this. Energy and societies, and it's strange that this is not more widespread, not here in the room, but I mean in general. In fact, there are very few chairs, I don't know, in the Collège de France with the title Energy and Society, probably. And this brings me to another issue that we could, a group like this, and the Academia Lincei and the Balzan Prize could push, is the idea that interdisciplinarity, yeah, I know nobody really knows how to do it, perhaps, but there is something which is called the environmental sciences, both the natural sciences and the environmental social sciences, which have been growing around the world. There are places in the world, in the Netherlands, for instance, or in England more, and the US, where you have university posts in the environmental social science with this denomination, in which you would have ecological economics, political ecology, environmental history, and these things, because of this kind of silo mentality of many continental universities still, doesn't happen, in which the positions open in the CNRS probably, I don't know too much about the CNRS, but also in the universities are on, I don't know, very old-fashioned ways of calling them, like scholastics or canon law probably no longer, but more or less the equivalents in the different kinds of law, the different kinds of economics and so on, but not into this interdisciplinary called explicitly environmental, social sciences, environmental, natural. That's what we do in our institute in Barcelona, that we did without telling anybody, just by getting European grants and so on, people from physics, from all this, because this one thing which is very practical and we could have. And the common thing, it would be energy and society, isn't it? And going back to what Alberto Quadricurcio was saying, I think there are moments in which there is a breakthrough in the thinking of many people in the world, and this was the early 70s with the Club of Rome and several reports like this. But I think there was a reaction. Politically, there was a reaction which was the neoliberal reaction, which was not exactly against the environment, it was more against Keynesian social democracy, if you understand. And Brunden, herself a Keynesian social democratic from Scandinavia, represents this kind of consensus on how to stop, in my view, the radical environmental movement, by saying we can have sustainable growth, sustainable development, everything can be brought together without deepening the study of the conflicts, of the contradictions between the economy and the environment. If we move into studying energy and society, we are leaving a little bit aside, and some people even in the room perhaps don't like it, the economic reasoning and so on. For instance, I am very glad that I am extremely glad that European Union has decided to move away from austerity, to move away from this kind of fiscal, more or less, and then to do Eurobonds, isn't it? Which means that the debts will be European debts, will not be Italian debts. So this is very good for Europe, for the idea of the European Union. So I was born in '39, so all the people, we are very pro-European, many of us. So this is good. But together with the green bonds, there is the fact that there are big financial interests who know that they are being sort of suffering from the fact that their assets are what is called financially stranded assets. So if you are the owner of a big oil company, or the shareholder, or the pensioners who have funds in a pension fund of a big oil company, or a big coal company or a more or less big gas company, you know that your shares, if this is true, that we're going to decrease by half the emissions by not burning fossil fuels, they're going to be much less. This is called financially stranded assets, and you lose the asset somewhere, isn't it? So this is very painful. This is why one sees in places like Glasgow the lobbying from the fossil fuels interest, isn't it? So this is one thing that we should bring into this kind of energy, and society has to deal with the economy, but not in the sense that we can grow as if nothing had happened.
Well, thank you very much for suggesting. You want to react? Yeah.
Yes, maybe if I can follow on your point, we have nowadays, this kind of big companies that you mentioned, fossil fuels, that are this kind of greenwashing, we call them. And the question that I ask, maybe for you, is how do you think that we are going to do this energetic transition with or without this company? Because you need money, and these are the companies that have money. So how you are going to handle this kind of stuff? Because the population sees them as kind of bad boys, but we need to have the bad boys to make the transition.
Well, can I say something very shortly?
Short.
At the level of companies, you have a Tesla, but you also have TEPCO in Japan, which is bankrupt, should be, because of Fukushima, should be bankrupt, isn't it? Which is another stranded asset. And there will be, so you have both things. Doesn't matter with companies. Companies come and go in a way, isn't it? Or this should be the rule. But the idea that you can have economic growth with technical solutions to everything, I am skeptical. That's the only thing.
This sounds all very good, but can I come back to initial question? What do you expect from the other side, the natural sciences specialist first? One of the problems we have all the time is first, how can we help our kids and the next generation to understand better than we did or others did, and what could be done to improve that? And my practical question to both Susan and Jean-Marie, what do you expect from the humanistic and social sciences part in terms of help to convince not only the kids, overall the politicians, because they do not always believe in natural sciences, they need some psychology, even psychiatry sometime. What do you expect from the humanistic side in terms of help? Very shortly, Suzanne.
Okay, very shortly, I think the young people, we saw many examples, the young people know what we're leaving them, and they're not happy. So I think, I go to classrooms in Rio Branco in, the far western Amazon, and they know about climate change. And they know that they didn't cause it, but they're experiencing it. So I feel like the education part is maybe not so badly done these days, but I think what we need to, it's this idea, we know agriculture needs to change. That 25% of our emissions are from our industrialized agriculture, and the fact that, we're supporting the soybeans that we grow in in this ranch in Brazil. They go to the Netherlands to feed pigs that we eat here, probably. So we have to change everything is connected, and we have to realize that and figure out which of those connections we value the most. And I think that's where the social science can come in and help, both to explain those connections to people so they can make choices, because they don't know, I think, where their goods are coming from. But also, maybe that's it. Maybe just to point out to the people the price of what they do.
Jean-Marie? Yes. Again, as I mentioned in my speech yesterday, I think we need to educate young people. And here I really want to share a very recent experience that we have done at the Collège de France. We have done, I think 3 weeks ago, a survey about 1,000 or 1,200 students. And the question was, what was contact or they thinking about science and climate change. And we asked them several questions. And to make the story short, they all aware of climate change is a serious issue. They all display some kind of anxiety against this kind of stuff. But then after, when you start really to try to see more or less what they really know about this kind of stuff and the real world, here you are a kind of deceived to a certain extent, because, for instance, I will really give you two answers to two questions. One question was simply, is climate warming has been demonstrated? 60% of the students answer, no, climate warming has not been scientifically demonstrated. Okay? Then a second question, for instance, was in terms of nuclear. What is more or less most contributing to CO2 emission? Is it nuclear or carbon? 48% answer is the same. So just to more or less to tell you the level of education. And I could go in several types of questions. And I think, again, as we have to think about this energy transition, I think we have to rethink how to educate the new generations. And then we went into kind of questioning about, what will be the best way to give you information? Should we have this kind of 1 hour lecture that we give at the Collège de France? 5% told us is useful, 95% they don't like it. And what they want, more or less, is kind of, speech, 5 minutes, 3 minutes, in which you can give information and so on. So looking at this kind of stuff, you can say, no, forget it. I think we have to react to it. And I was thinking myself, even thinking about really creating a kind of dictionary about what are these wordings that we are using today. When we talk, about CO2 taxes, when you talk about different technical terms, what is a charge of each windmill panel and all this kind of stuff. This stuff is strange. So I think we need to have really a large amount of work. Reason why I think all these people from social economists and so on have to be a part of the same table, and we need to think all together how we can make a useful language to the students. So this is my whole belief.
You didn't say anything about the teachers. What is the role, or how can we educate teachers? Johan?
Yes.
I think.
Thinking here, well, let me just in this morning, for instance, when Susan was saying that whether the Amazon in Brazil, which is not a small thing, isn't it? And now I realize that you teach in Rio Branco, which is near where Chico Mendes was still defending the forest and so on, as you know, not because of your university training, because traveling you learn. Anyway, the question is the Amazon emitting more CO2, the forest, than it's absorbing? Which is a very crucial thing.
Do not forget to speak about the teachers who's teaching our kids.
I am a teacher myself, we are all many teachers. This question that one can, a teacher means that is showing the important things, not how they have been answered already, putting the questions. And this will be and the other thing, because in my atlas we have lithium conflicts in South America, as I said, in Spain. So from him, I've learned that perhaps sodium batteries are going to come, isn't it? And lithium conflicts. So when one has to do a thing in teaching is to be open to the other sciences if we are in the environmental field. And not to say, I am economist, and I don't know what a kilowatt hour is because I am an economist, to put it in a very ridiculous kind of satirical language, isn't it? But this happens. This happens with the scientists. So to expand your ignorance.
Okay, but again, I think we need to exchange between us, because you say sodium ion and lithium ion. I don't want to give the message that sodium ion is going to replace it. It's just an alternative that can help. And I think we need to have this kind of discussion to put things right. Don't oversell things and put it right. Sorry.
How do you think we can deal with the insecurities of science? Because in the whole COVID crisis, I think that is one of the things that strikes me most, how difficult it is to convey to the public at large what it means that you have certain insecurities in both the natural sciences and the humanistic and social sciences. And I think it's very important not to act as if we have only securities, and we don't. So I was wondering how you are thinking about that.
I mean, by insecurities, do you mean the risks, or?
I mean, insecurities about interpretations. You said in your presentation, for instance, how you found the models for the Amazon developments too optimistic, but it's not a sure thing, of course. So.
But I can step back and say the more important question, I mean, it's irrelevant almost what we do with the land surface, because the fossil fuel emissions are the things we have to change. So I can step back. There are lots of reasons to care about the biosphere, biodiversity. You know, we can't eat fossil fuels directly. We have to grow something to eat from them. So, so we need the natural world too. But in that particular question, I can step back and say, you know, the most important thing is to cut fossil fuel emissions if we want to reduce the risks that are associated with climate change. So, I mean, it's the analogy is we're driving towards the edge of a cliff. We don't know if it's a really steep one or a really shallow one, if we'll survive or not. But you know, the smart thing to do is put on the brakes.
Yeah, so you make a distinction between what you can say and what is more hypothetical. And,
right, and well, and what needs action. What can you say that with certainty versus, you know, yes, the Amazon may or may not be a source of carbon now, and the people who care about that are the people who have to pay or not carbon, you know, a cost for the carbon they take up or release. So it's a political question more. But in the large scheme of things, you know, it's still maybe 5-6% of the total biosphere sink that we're talking about, and you know, that's a very, it's not going to stop by itself the rate of carbon accumulation in the atmosphere. So.
I think, you know, again, the risk of science, I think we need to teach them correctly. And I think we are in a beautiful timing. You know, when I should give a class of chemistry today, I should say, you know, look, guys, look what COVID-19 was, and look how scientists very rapidly were able to solve the issue. And I think here we can, and then after, here we have risk. Again, I go back to nuclear. What are the risks of nuclear against the risk of COVID-19? You need to put things in perspective. And at least you need to show them the reality, what are the scientific issues, and that science doesn't happen a single figure, takes time, and again, but looks at all the wonder of science. And I name this one, okay? I could have named and look back at history. Of course, they have a special case, but we should put things in perspective and not give kind of black, you know, picture of what we are doing. I think it should show some excitement, passion, and with reality.
I think the comparison with the pandemic situation may be interesting. Now, the pandemic situation is not closed yet, so we are still with a lot of things which are not clear, how we get out of it. With the energy is similar, with the battery is that similar. I mean, when Marianne mentioned insecurity, I was also thinking about, do we get there where you said just a few minutes ago or hours ago, that the batteries will have a much longer duration, that we will have less pollution with producing the batteries. How do you go there with saying what is clear today, what you hope will be there tomorrow? Is it better not to say what is not clear tomorrow?
No, I think more or less, you know, I can answer this question in two ways. First way that I will say, you know, simply look at the progress. For instance, you know, took about 150 years for the battery. We talk about lead acid or double the energy density. You take lithium ion, took about 20 years to double. And I think now we have a mature chemistry that have, of course, few incidents, but we have a progress, and I think with all the new technologies that we are putting together, definitively we are going to increase continuously the more or less lifetime, lower the CO2 footprint, but we will never have a zero risk, because again, we are putting energy, and I don't want to scare you, but if you look at the battery clearly, it's small bomb. You are trying to put energy in a very small confinement. So we need to look at this kind, and I think there is nothing to be scared about it. And we talk about lead-acid batteries, but you know, lead-acid batteries have issues. You know, there is hydrogen evolution, and kind of, you know, high communication plants. Some lead-acid batteries 30 years ago, 40 years ago blew up, but we don't mention about it. Okay, so you have these kind of issues that you need to take into account and put in perspective when you are really teaching, communicating with students or with young people.
Well, but you know, what I think with the pandemics that we have all learned about pandemics that only some specialists in history remembered, and the Spanish flu and so on, and the pandemics in America, which meant the depopulation of America after the European conquest, or many regions of America, and then the Black Death, and so on. So although our history is a history of pandemics, in fact, we had forgotten many of us, and this is in a way similar to the fact that the risks are perceived quite often too late, isn't it? Even Columbus had no idea, perhaps he didn't care, but they caused the depopulation of America 90% or so. And this happens with climate change. Climate change, we know that scientifically, Arrhenius and so on is known for 130 years already. And how do you explain with your theory that risks are assessed, the fact that many people have taught economic history, including myself, during many years, saying a history of progress, isn't it? Watt invented the steam engine and the cotton machines, and then, well, a little bit of slavery in America brought cheap cotton to Europe, and it was a history of success, a history of our success as Westerners. And right now, if you have to explain economic history, and there are some books like Andreas Malm, for instance, the first picture in the book of economic history is the killing curve. And saying, how didn't we know this? I mean, so the first picture in the book is the killing curve of the carbon dioxide emissions. And one could ask, how is it that not only economists, normal people from, well, this is a long time ago, it's the end of the 19th century, so why people did not put this as the first lesson from secondary school to university, that this was going to happen. And what happened is that Arrhenius himself, in his first article, I always joke that he was living in Stockholm, perhaps he was in winter, and he said a little bit more of heat would be very convenient. And because the frontier of cultivation will go a little bit to the north. And now we know that the heat is going so much to the north that the methane in the tundra is going to... So, apart from the ignorance and this kind of retrospective jokes, which in fact they have... But the point is that it's difficult to assess probabilistic risk of something, new technologies in the future. And that there is a bias, which is not the fault of Galileo or the Lincei Academy, because they were telling truth to power, or to the cardinals and the Pope. But to mix the scientific progress, to assume that this brings technological progress is a big jump, I think. Because some of the technologies, we don't know beforehand the effects that they might have. And with nuclear, which we could discuss much more, since it was linked to the military from the beginning, so it's difficult not to realize this, that one thing is the science and another is the technology, isn't it? Although some people who are more radical than myself would say, no, we know that the scientists are being paid by the technologists. I don't believe in this. I believe that what you do comes from your brain, not from your pocket, isn't it?
We all believe that. Can we... If it is short, why
No,
not?
very short. But
Well,
I
you
just,
said discussion between...
short, because I think you're perfectly right, and I will put it back into history. Because you look at sodium ion, you look at Jules Verne, Nobel, 150 years ago. He said, sodium ion batteries should be the future. And even talk about hydrogen, which will be the earliest sources. So you have a vision, risk, and technology.
So history has definitely the place in the natural science, Mariam. Now I would like to ask you, who would like to have the question? Yes, Giselle. Microphone.
Thank you. I'm not really a scientist, and I want to thank you very much for your very interesting contributions that let me feel that I understand what you are saying. And I would like to add an additional dimension in your discourse, and I would like to be very interested to hear your opinion about your relations, of course, with the financial market, of course, with economy or with the people, but especially about politics, because politics has something very special in addition to all the other players. They are very short, terminated, I don't know how to say this exactly, but they think very often in 4 or 6 years of time. And how do you think is the quality of your relation and the impact you might have on politics or politician? I think the dictionary that you want to do for the people would be very useful also for the politicians. Thank you.
Suzanne, you just had elections, so your influence on the elections and afterwards?
I had no influence on the elections. I mean, I feel, on the one hand, the positive thing that I see is that there is a COP26. I mean, for Earth system science, the successful version of this was the Montreal Protocol and the reduction of the chlorofluorocarbons that, we would have been in trouble by now had we not done that. So to me, the hopeful thing is that the world came together, even if it didn't do everything perfectly. So, I mean, I don't know how to communicate better unless we get ourselves involved in political office. I think the people who are running for office maybe are interested in different aspects and maybe not so thinking, as you say, long term. I think we do need people who are allowed to think longer term, because these are not 4-year questions. They can't be solved in 4 years. So, Stuart wants to
add. I think I will be very short. We don't have too much interaction because we are not in the same time frame. We don't understand each other. This is more or less an issue of time frame. And we are in a 10 years, 15 years time frame because the research, technology take time to develop. Politicians are in a 5 years time frame. So we have difficulty to adjust, and they have difficulty to take risk. So it's on one, more or less, we don't have this kind of, there is a gap. How to fill it? This is a good question. I don't know. Tell you the truth.
It's for the vision.
Yeah, but...
No. I think that politicians have to show that they are secure that what they say is important and true in a way, because they're competing in the elections with some others, or even when there are no elections like in China, they have to say convincing things in a way that looks really that they know what they are saying. And normal people, like especially scientists, when we say something, is rather tentative, isn't it? We're not, myself, I'm not quite sure of what I say. Well, I try to say it very clearly, so that competing with some other visions, perhaps somebody, and the politicians talk in a different way. And this is very common to one sees example after example of this saying, we'll do that, and it's a big difference. It's not only time frame, but also...
Yeah, just an example, 30 seconds.
Yes.
Look at France. The elections are coming, okay? We were kind of against nuclear 5 years ago. Suddenly now everyone is going to go for nuclear.
Not.
Why? Scientific were still here, and I think they have reports.
What did you do?
Nothing.
See it, clothing.
Yeah, I'd like to follow up on this point raised by Giselle. We have heard also earlier this morning that in some cases Europe takes the lead. This is also the case in the domain of scientific advice for policy making. Here, the European Commission has established a few years ago the scientific advice mechanism. We have a group of 7 chief scientific advisors, but working together with a consortium of academies in Europe, including Academia Europaea, addressing questions posed by the Commission on a whole variety of issues where they want to know where is the science standing. Also for legislation. Same comes from the European Parliament. The topics include topics like food from the oceans, energy transition, but also aging Europe. Also issues like biodegradation of microplastics, issues like making sense of science, in other words, living with uncertainties. The European Commission wants to know where we are standing and is fully aware of basically that its advice. Options are given with pros and cons. In the end, the democratic process makes the decision, but the European Commission is highly interested in this, and this mechanism will be further prolonged and expanded in the coming years with the new Commission. So there is basically not a kind of uniform pattern of a misfit. We have success stories here, and I can see also that this model is also being exported to some countries which so far were devoid of a mechanism of scientific advice. Of course, we also know that it's dependent on who is there in the government side. It's very clear that the new government in the US is more prepared, let's say, to ask for advice. So what is very important is the issue of trust. There must be mutual trust between those that have to make the often difficult decisions and those that provide ammunition, basically, to know where is the science base. And also in some cases, it's very clear that this mechanism has also revealed gaps in the science base. Like in the issue of the biodegradability of microplastics, it's very clear that the science base is incomplete. Nevertheless, the Commission has to take decisions. And they have to know where are the gaps. But I think that's why a panel like today is extremely timely. And again, there is work in progress. There is also some best practice being developed. And I think it's very important, of course, that also the topics that I just mentioned are all topics where you can say they need input both from the social sciences and humanities and from the natural sciences and from the life sciences. And that's exactly how we compose the working groups of experts with input from engineering, from life sciences, from natural sciences and social sciences and humanities. In that context, what is happening here today is extremely relevant.
Thank you very much, Siert. Would you like to react on this, or can we move to a last question, because I think lunch is approaching?
Maybe, yeah. Just maybe I fully agree with what you say. I think Europe is taking the lead. I think it's a locomotive on these topics. And I think we can have more influence at the European level than our national levels. For instance, in the type of research that I show here, this is part of Battery 2030. And I think where Europe is less good at it is really try to put the tools and how we are using the tools. I think it's our fault that we don't use the tools right. And I think also Europe is not good enough in commercializing our really advanced or technological advance. But I think they are great and put in the directive and so on.
So maybe just very quickly, the Intergovernmental Panel for Climate Change, I think, is an excellent example that scientists from all countries could come together and be trusted because they were from all countries. It wasn't just the North telling the South what was what. But also they went from just the physical science basis to Working Group 2 and Working Group 3, which were, what's the mitigation and adaptation, how is this going to affect individual places and countries, and it allowed things to plan. So I think it's the same idea, that we need these independent scientific bodies that...
The only thing is that I think in politics sometimes you have to give slogans which are convincing. One example, well, there are two examples which I have lived in my life. One in the advisory committee in the European Environment Agency on biofuels. There was an enthusiasm for biofuels. I remember Helmut Havel from Vienna, myself, trying to, let's write something against it, because we understood that biofuels means loss of biodiversity in Brazil or in many places, because it means more soybeans, more sugarcane, and so on. And this was very difficult because there was like lobbies which were pushing for this. And it's very easy to dismiss scientific opinions and all. And the other is the circular economy, which is so fashionable and comes from China, from the law in China of 2000. Well, it's like, well, it would be more appropriate for a religious group of people to say the economy is going to be circular through a miracle than as a policy, because we are so distant from this. Or perhaps one can reinterpret it, but scientists, we don't, in general, respect the consensus. In fact, we live from breaking the previous consensus on many things, isn't it? I mean, the big scientists, the ones who discover something new, change the paradigm, isn't it? And this is something which politicians, sometimes in Europe especially, like this consensus. And there should be room to be a dissident of this kind of thing. There is in Europe. Even in the ERC, I think there is room for this.
Yes, it sounds relatively optimistic what you said, Sir, but I think it's very important. But beside the European approach, I think we still need the approach in each of our countries. Switzerland is, anyway, a little bit outside, but I think the national context, as we see it with other problems and questions in Europe, is also important, and there it would be very important, as you said, that panels like that try to make a good, solid scientific basis, and then add maybe some national specialities on it to convince our national politicians, which are still, not only in Switzerland, I guess all over Europe, they are elected nationally for most of them, and sensible to a national approach from the citizens and the scientists.
I would like to invite you to continue the discussion while having lunch. And do thank, first of all, our prize winners for not giving only very interesting presentations, but also willing to be here and discuss about interdisciplinarity in a very concrete way. I think it encourages us of the prize committee to continue on what we think will be our road to do more interdisciplinary research, but also to support all sorts of projects who do really interdisciplinary work. So thank you very much. Thank you, audience, for your patience.